Good day and welcome to the X.Org Developers Conference 2021. I'm Rashad Knop, your MC for the next 3 days, and we are starting right off the bat with the opening session from Radek Schwichtenberg. Radek, the stage is yours.
Hey, hello. Welcome to the X.Org Developer Conference 2021. Again, virtual, bringing some great talks this year. The program is excellent despite of the conference being virtual again. And before I jump into some details and some tips on how the conference will be handled, I'd like to start with saying big thank you to our sponsors. That without them, what we do here wouldn't be possible. So let's start with our platinum sponsor. Big thanks for Intel for being platinum sponsor for a second year in a row. Big thanks goes to our gold sponsors, to Google, NVIDIA, ARM, Microsoft, and AMD. Thanks a lot. We also would like to send big thank yous to silver sponsors, Igalia, the Linux Foundation, and Collabora, and of course to our bronze sponsors, GitLab and Kronos. This year, we have new streaming experience that we are trying for the first time. That is brought by our supporter, C3 VOC, providing Media CCC streaming this year. So thanks a lot for this support, and I hope everyone will enjoy it. I'll have some more details on this going forward. The organizing team this year is again Intel and X.Org, so big help, big help from Intel on this side and X.Org for getting all this being put together. So big thank you for our organizer this year again. Some useful information. So we have 2 ways of attending the conference via live stream. We are streaming live to YouTube, and we are also streaming through the streaming service I mentioned a second ago. So please visit our website. There are all URLs available there. Follow us on Twitter. We'll be posting all the latest information and what is happening there. So you will be up to date all the time at what is happening on XDC, hopefully. If you have any questions, you can reach out to the organizing team on OFTC IRC on our channel. Nicknames listed. All this information is also on our website, so make sure you find some time to check it out. So streaming, in addition to YouTube, which probably everyone is familiar with, as we did that last year, we are bringing some new experience this year with Media CCCDE. And links are also shared already on our webpage, but there are some new functionality. We are super excited that this non-proprietary service is now tried out on XDC. So check it out. It has built-in timelines and schedule for the conference. So hopefully this will be a new exciting functionality that we may be bringing in next XDCs as well. We'll see. This year, as last year, we will be allowing everyone to create hallway discussions on our Jitsi instance, and feel free to use it. It was slightly underutilized last year. And we believe that XDC is not only about the talks that we have or our streaming, but also about people having live discussion on what they heard on the conference or so on the conference. So we will be supporting this. Make sure that if you create a room for informal discussion or some discussion about the topic that was presented, share the link on the IRC channel and invite some attendees to join. We will be supporting it throughout the entire conference. So in case of any issues, reach out to the organizing team. The program, entire schedule is available on our website. And the same tip as last year, if you would like the program to be visible in your time zone, you need to specify this on Indico. Otherwise, it will be visible in organizer's time zone. So it is UTC +2, so Polish time zone. We are still allowing lightning talks, demos, and workshops to be added to the conference program. Don't forget to keep any notes you have from hallway discussions or any other discussions, presentations, workshop, etc. We will still be allowing them to be presented on Friday afternoon. The rules are, as always, 5 minutes for lightning talks and 10 minutes for a demo. We do have a significantly higher number of workshops this year, which we are really happy about. So thanks for submitting those workshops. We still will be allowing, as you know, our schedule permits, adding new workshop. If you want to do so, please reach out to organizers. Workshops are visible in the schedule as those big orange boxes. So if you would like to read about what the workshop is about and reach out to the workshop organizer driver, make sure you reach out to them and ask them to be added to the discussion, because this will require you to join the Jitsi instance or Jitsi room where the workshop will be handled live. Speakers, after your talk, please help us having all the materials, the presentations shared with our attendees. To do so, you need to go to the XDC website, go under your talk and use this small button in the bottom right corner to get the talk uploaded. And if you have issues, again, reach out to us. But this is very important for us that you as a speaker supports the community and share your slides with us. Code of conduct. This is something that we always find really important on the events that are organized by X.Org. So we are dedicated to providing harassment-free experience for everyone. We do not tolerate harassment, and we will be actively working for it not to happen. So more details are available, and the entire code of conduct for you to read is available on our website. In case you see any breaches in code of conduct, we have a committee, code of conduct committee again this year. Please make sure that you contact any of the listed people. The same list is available on our website. You can also reach out to us on IRC. Of course, it's 2021 IRC, not 2020. And yeah, we do not tolerate harassment. So make sure that if you spot something, you let us know so we can help handling it. That's all from my side. I hope everyone will have great experience with us this year again. And thanks again to all our sponsors, and have great first day of the conference and hopefully the entire 3-day experience. Thanks everyone, and see you around. Bye-bye.
And we are ready to go with the first talk of the day, Iago Toral's presentation on the Raspberry Pi Vulkan driver. Please welcome Iago Toral.
Hello, my name is Iago Toral. I work as a graphics software engineer at Igalia, and I'm one of the developers of the Vulkan V3DB driver for Raspberry Pi 4, which we presented here at XDC last year. And today's presentation is going to give an update on what we have been up to for the last 12 months and where we are today. So this is the structure that I prepared for this presentation. We are going to start with a very quick recap of where we were a year ago. And then I'm going to detail what has changed since then, what new features and improvements we have brought to the driver. One of the areas in which we focus, especially in the first months of the year, was performance. So I would like to go in details there and explain what kind of work we did and what kind of results we achieved. And then I would like to finish the presentation with some thoughts about things we might be working on for the next 12 months, maybe. So starting with a quick recap of where we were a year ago when we presented at XDC the driver for the first time. We had a minimal Vulkan 1.0 implementation. And when I say minimal, I really mean fairly minimal in the sense that Vulkan 1.0 allows for many optional features and, of course, extensions that we just didn't have. We were also not conformant at that point. We were kind of getting very close, but we were still at the point where we were kind of squashing the last few CTS test failures. We had not merged the driver in the upstream Mesa repositories yet. We were starting discussions. Actually, I think we started discussing this with upstream right after XDC. And one of the issues I mentioned we had was that the driver was still fairly immature in terms of actual testing. We had been testing with CTS, and we had been testing with some relatively simple games such as the Quake Classics or other demos such as demos from the Sasha Williams repositories. But we had not been able to test with more modern applications and games, if you will. And a good part of this was related to the fact that we were still getting there with the driver and focusing on just developing the features and not so much as not so much testing yet. The other part of this story was that the reality of Vulkan and applications and games available for Linux ARM wasn't really that great, right? So that was one of the issues we had at the point. So fast forward 1 year to present day, let's see where we are. So obviously some of the things that are probably well known by this time is that we merged the driver upstream, and we have been developing upstream ever since. Another thing we did is to integrate our internal CI with the upstream GitLab CI. And this has been very nice for both the OpenGL and the Vulkan drivers, not only because it makes regression checking a lot easier and preventing regressions a lot easier, but also because it makes it easier for external contributors to test their patches before sending them for review. And the other thing we did, of course, was to obtain Vulkan 1.0 conformance. And I think this will happen either before the end of the last year or very early after. So other things we've been working on is Vulkan 1.1. So we currently, I think, have a minimal Vulkan 1.1 implementation, which again is not yet conformant. We are working on finishing the last test failures that we have. We have a few flaky tests and things like this. So I think we are not very far from being ready to to clean conformance. So hopefully this is something that we will be able to achieve soon. We have also been getting a bunch of additional extensions and optional features that our driver can support. Some of these were also contributed by external developers, which is great. We also have better Windows system integration these days. And again, this was thanks to external contributors. Particularly, they provided support for Wayland and Direct Display, which is also very nice. And as I suggested before, we have been working on improving performance, and there have been some significant improvements in this regard as well. So another thing that we got working is RenderDoc. So RenderDoc was actually working, I think, 1 year ago, but there were some annoying bugs that kind of made it difficult to use in practice. So we did manage to get this fixed, and at least in my testing, I think it was working fine. We also got GFX Reconstruct, which is this tool that allows you to save traces from a game and reproduce them afterwards. This is something that we got working for our own purposes, as I will describe later when we discuss performance. But it's a useful, really nice tool that's available for developers, and that should be working fine as well. And I mentioned before that one of our issues last year was the lack of real-world testing. In that regard, I think we also made some improvements. We were lucky enough to get our hands on some Unreal Engine 4 samples, binaries that were compiled for the Raspberry Pi 4 by some other people who made them available to us. And while these are still, just small demos, they were useful in testing our driver with more modern workloads, and we are happy to report that these are working fine. And they were also very useful to drive some of the performance optimization efforts that I'll discuss later. So, as you can see, there's been a lot of new things happening during the last year. And as I mentioned, one of our focuses for that period of time was performance. So let's see a bit what we did there. So as I said, we got our hands on some Unreal Engine 4 samples, and this was for us a great opportunity to use this more kind of modern game code to test how well the driver was doing. And what we found is that we were generally GPU limited, which is, I guess, what you would expect and what you would want when you are developing a driver. You do not want to be CPU limited because that could point to issues in the driver. So I think this was ideal. At least at first. I think there was only one game that at some points was CPU limited, and it was this racing game that is there on the bottom right section. The issue there was that that game was emitting a very large amount of occlusion queries, and our implementation for that was not optimal. So we improved that, and kind of that got rid of the CPU limitation. I think that's basically the only case where we were CPU limited. So generally, we were GPU limited, and what we found is that these Unreal Engine 4 samples were a lot more expensive in terms of shading than anything that we had run through the driver before, which makes sense, right? So we focus most of our performance work, not only, but most of it, and at least the part that I'm going to discuss here on the shader compiler, which is great in the sense that all the optimization work we did here was not only useful for Vulkan, but also for our OpenGL drivers, because we share the shader compiler, basically. So in terms of performance, what we did was, the process is very basic and probably what you would expect. We basically capture generated shader code from these Unreal Engine 4 samples. We try to identify not optimal code traces by eyeballing these captures for a very long amount of time, really. So once you have identified non-optimal code traces, you have to trace them back in the compiler stack to understand when and why they are generated. And then you start designing and thinking about ways in which you can do better code generation for these situations. And after you have an implementation for a particular optimization, then you need to find a way to verify the results. And here's where things sometimes get tricky. Sometimes the optimizations are like produce very obvious results, and you just run the game, and just the frame rate is just better, right? It's obvious. Even for Unreal Engine 4 samples, which are, at least on our platform, have a wildly varying frame rate behavior. Like I guess Unreal Engine is doing its own thing under the hood, and even if you are not modifying anything, even if the camera is static, nothing's going on, nothing's changing, the frame rate can suddenly drop or increase for no obvious reason. But beyond that, there are like other issues, like sometimes the performance optimizations are not so large that they kind of get lost in the nose of the frame rate variance and things like that. So in some cases, it was relatively easy. Some of the demos have a more stable frame rate than others. But in general, so what we did to verify the results was a combination of manual testing in some cases. In other cases, we would just capture traces with GFX Reconstruct and reproduce them with GFX Reconstruct to make sure, basically, that the workload we were testing was exactly the same, and then we could easily test the patch against them and see the performance output difference. And of course, we always have ShaderDB, which, for those who don't know, is this large collection of shaders from various games that we can run through our shader compiler and extract stats on the generated code to see how we are improving or regressing on various fronts. So in terms of what we actually did, so as I said before, all these Unreal Engine 4 samples have in common that the shading is fairly expensive, at least in comparison to other things we have seen before. So for example, it was very common for many shaders to have upwards of 60 memory accesses from a shader, which include texturing and UVOs, for example, per pixel or per vertex. So that was kind of high, and we suspected that that was a bottleneck for our platform. So the unit that was involved with that is called the TMU in our platform. And one of the things we did there was better pipelining of these operations. So typically we would just emit for example, a texture fetch operation, and then we would switch to another thread, which is the way that our hardware allows us to hide latency from the texturing operation. And then as we return from that other thread, we would immediately try to retrieve the result and stall automatically if the result was not there yet. So we could do a bit better and try to queue. In some cases, there are restrictions, but in some cases, we can queue more than one TMU operation, for example, and then we could try to do better postponing actually accessing the result from that texture operation until it was absolutely necessary to try and hide the latency better. And that provides some improvements, but maybe not as much as we thought it would be. I think we got something like 3 or 4% improvement from that in some of the samples. What did make a huge improvement, though, was the fact that we realized that some of these UVO operations are typically constant across all SIMD lanes, which basically mean they are uniform loads somewhat. So for this kind of fetches, we can use a different mechanism in our hardware that provides or has the capacity for sequential reads. It has the capacity to provide us with a 32-bit value, uniform value per cycle, which is much better than what we can get with the TMU. So there is some setup every time that you want to fetch with this mechanism. But the key here is that many of these UV reds usually fetch multiple 32-bit sequential values. So for example, if you're loading a vec4, you are actually doing 4 sequential scalar accesses to memory, which is perfect for this mechanism. But beyond that, even if you have structures in the UVOs, it's very common that applications read them sequentially. And even if they don't, our compiler can reorder some of these to make them sequential. So by using these and optimizing this process as much as we could, we saw up to 20 or 30% performance improvement with some of the shader workloads and with some of the samples, which is a huge improvement. Other things we've been working on have to do with the capacity that our hardware has to emit multiple instructions in the same cycle. So there's, of course, a number of restrictions that could prevent that, but we found that our compiler was in some cases being too conservative with this. And so improving scheduling flexibility for that. And it was kind of important to improve this. And the other thing we did is there was a bug, I think, that was preventing us from merging instructions as much as we could, that I think only by itself improved code generation by 4 or 5%, I think. So the other thing we noticed is that all these shaders had a lot of variance between the vertex and the front-end shader stage. And our code generation for smoothly interpolated variance was not really optimal. So in theory, when we have a smooth interpolated variant in our platform, we need 3 instructions to produce the final interpolated value. But if you are using the hardware optimally and pipelining these instructions properly, after the first variant, you can produce 1 per cycle. But for reasons that go beyond the scope of this presentation, this wasn't happening. And we were only able typically to produce 1 every 2 cycles. So when you have a lot of variants, such as in this kind of workloads, that was also a hit on performance. And that's something that we also managed to improve very significantly. And these are only some examples. There were many other smaller optimizations that we did here and there that also contributed to improving the overall performance. But I guess this gives an idea of what were some of the main things we did. So how does that translate to actual results? So in terms of shader DV improvements, I just put here some of the what I think are some of the most important results. So the first row here, we improved thread count by a bit over 1%. So threads, as I said before, is the mechanism that our hardware has for hiding latency from memory access from shaders, such as texturing. So increasing the thread count here is better. It's a good thing. And then we reduce the total instruction count by 9%, which is a huge reduction, really. It basically means that on average, our shaders are 9% smaller in code size, which means obviously that they require less cycles to execute. Another thing we did is to reduce uniform counts. So there is a lot of state in our platform that has to be consumed by the shaders through uniforms. And this is for OpenGL in particular. This is one of the main causes of CPU overhead, because every time that you have a draw call that needs to change some of its uniforms to represent a state change, you need to rewrite the entire uniform stream for that draw call. So reducing uniforms helps alleviate this and reduces CPU overhead. And we also, even though we haven't identified this to be a huge cause of CPU overhead, at least with the samples we've tested on the Vulkan driver, a 6% to 7% reduction is still very significant. And even if it doesn't help as much on Vulkan, it should definitely help the OpenGL driver. And the other thing that I put here is spill and fills. As you can see, there's also a significant reduction for these stats as well, which means basically that we are spilling less and using the register file that we have available more efficiently, which is great. So the next question is, how does this translate to actual game performance? I have here a bunch of different games and samples that we have been testing with. And on the y-axis, you have frame rate improvements in percentage. So as you can see, there are improvements all across the board, no matter what kind of, but the larger improvements happen on the Unreal Engine 4 samples. I have two, the third and the fourth bars here are the shooter demo from Unreal Engine 4 with low and high-end settings, respectively. As you can observe, these are the two samples that got the most benefit, which makes sense since these are the samples and the shaders that we use to drive the performance optimization efforts. These are also the most complex shaders in this collection of samples. So it also makes sense that they are the ones that have the most opportunities for being improved by these optimizations. But the nice takeaway is that the improvements are really seen all across the world. And as I said, we would expect a significant part of the optimizations that we did to also benefit the OpenGL driver to a similar extent. So there is a caveat with all the performance work that we did, and it's that many of these optimizations have a cost, which is it comes in the form of increased register pressure. So in order to kind of alleviate this, what we did is to have a mechanism by which our driver can try really hard to disable certain optimizations when it needs to spill, basically, to compile the shader. So we have a mechanism that can iteratively disable optimizations that are known to potentially cause additional register pressure, with the hopes that we can produce the best form of the shader possible that doesn't spill. Now, I should say that this increases compile time a little bit, which was already an issue. In fact, you can see with any of these Unreal Engine 4 samples, I was a bit surprised actually about this, because these being small samples, I would expect that Unreal would just compile all the pipelines before the gameplay loop, but it doesn't. It does compile some pipelines. In fact, as soon as you move the camera, it will compile some pipelines, and you can see the game freeze when that happens. I mean, this was happening even before all these optimizations, and this was just making it even slightly, but even if it's slightly worse. So what we did to alleviate this was to implement the disk cache, which works really well. It won't help you in the first playthrough, but definitely helps in playthroughs other than the first. This is something that we did only for the Vulkan driver for now, but probably it's something that we might want to do for OpenGL as well in the future. I would also like to comment on a few, I guess, lessons that we learned from this process. One is we initially have been working on I think this was work started by Emma, on a near scheduling implementation that was useful. It gets some of the job done, but we found that maybe near is not exactly the best place if you want to really, get the most of the scheduling. For example, our near scheduler at present tries to separate as much as possible all the texturing from all the texture. I mean, texturing from when you actually use the results, which makes sense, right? You are trying to hide the latency, but it doesn't account for the fact that there are limitations in how many texture operations we can queue and how much register pressure this can increase on our target platform. It has some heuristics to try to kind of balance these two things, but in practice, they don't always work really well. I think by doing this at the VR level in the future, we might be able to do better. The other thing we saw is that producing better VR, which, by the way, is like an intermediary representation of the shader code that is very close to the assembly, but not quite there yet, but it allows us to incorporate some of the hardware semantics into it. So sometimes we do an optimization that produces better VR, but we ended up producing worse QPU code, which is the actual assembly. And this was because of register allocation. It turns out that in our platform in particular, register allocation plays a fundamental role to allow for our capacity to merge multiple instructions. So depending on how register allocation worked for a particular code, sometimes it would actually lead to worse QPU, even if the starting point was better. We actually fixed, or at least I think we improved some of the heuristics involved with register allocator, which, according to shader, produce clearly better results. But before we did this, we actually dropped some of the optimizations because of that. So I think in the future, we might want to revisit some of them and see if our register allocation and QPU scheduling is now up to the task to really make good on the better fear. And then I mentioned how we are now having multiple compiler strategies that iteratively disable some optimizations to produce the best version of a shader we can possibly produce. But these are not, I mean, this process is not always optimal, and sometimes this is not exactly what happens, because we kind of assume that if we have high register pressure and we need to spill, and we disable this optimization, which is likely to produce higher register pressure, we are going to have a better version of the shader that does less spilling. And that's not always the case. So I think we could even do a bit better by trying to sometimes remember what was the best strategy instead of always assuming that the next strategy is going to be better. All right, and so that's it for kind of the performance work we did. And now we would like to discuss a bit what may happen in the future, what are our plans for the next year or so. Now, this is still very early stage. Nothing of this is confirmed, but here are some early thoughts. So obviously, we have Vulkan 1.1 conformance in our sites. We are finishing up work for that. I hope we can submit this before the end of the year. We know we still have a large backlog of optional features and extensions that we haven't implemented yet. And it would be nice to focus on this. We had a few requests for some of these to support emulators and things that people may like to use with our driver on the Raspberry Pi 4. So we would like to support that going forward if we can. It might be interesting to try to understand how medium P 16-bit could improve or not our performance, our register allocation process. I would like to investigate that a little bit. Generally, we would also want to work on performance a little bit more. I think there's always things that you can keep improving. We also, I think this is important at this point, improve our kernel interface. So when we presented the Vulkan driver a year ago, we mentioned that we were reusing exactly the same interface that we use for the OpenGL driver. And this doesn't really match the semantics that Vulkan has perfectly. And because of that, we are limited in some ways where I think we don't want to continue being limited. And this affects performance, but also some hacks that we had to do in the driver. I would really love to see some of these gone and improved. And then maybe, of course, we could always start thinking about Vulkan 1.2 once we obtain conformance for 1.1. I don't think this should be an immediate priority for us. I would rather focus on, as I said, supporting more extensions and features than focusing on Vulkan 1.2. But of course, this is always going to be a possibility. So, and that's it for this presentation. So if you want to stay in touch with us, reach out, ask questions, whatever. You can talk to us at the video core channel of TC. We are also on the Mesa Devil mailing list. And of course, you can file bags or feature requests on the Mesa GitLab. And if you want to just follow development progress, both Alejandro and me usually blog every now and then about that. So you can just follow our blogs. So that's it. I think we have some time for questions, and if you have any, I would love to try to answer them as best as I can. And I would also like to let you know that ICALI is always seeking out people who are passionate about free software, about Linux, about graphics. So if you would like to work on this stuff, just let us know, and we would love to know about you. So that's it. I hope you enjoyed the presentation.
Okay, and we're ready to go with the QA session. Welcome, Jagtrell. And now we have a few questions here from IRC. The first one is from Eric Engstrom. What's a QPU?
Okay, so a QPU is like the shader core in the Raspberry Pi Broadcom GPU. And we also use QPU to refer to the native assembly of the QPU processor.
All right, another question from JMS. What's near and veer scheduler?
Okay, so near is just a representation of the shader code that it's translated by Mesa. So we get the GLSL or SPIRB code from the application, and it is translated into a different representation, which is near, which is then used to optimize and run a number of lowering and optimization passes. And the scheduling aspect refers to decisions that are made at that level about the ordering of the instructions. So which instructions are emitted early, which instructions are pushed back. And this is, for example, done to hide latency from texturing operations. So if you have a texture operation, and then later on you use the result from the texture operation, the nearest scheduler will try to put the texture operation early. So you have instructions in between the texture operation and when you actually use the result to hide the latency from that operation. And what I mentioned there is that instead of doing this at the near level, which is completely hardware agnostic and doesn't understand many of the concepts of the underlying hardware, we would probably like to do this at the veer level, which is a different lower level shader representation that knows about the target hardware. It's specific to the Broadcom GPU, to the B3DB driver. And there we can incorporate additional semantics that can allow us to do scheduling better.
All right. Bas Nieuwenhuizen asks, any plans for a Kronos Vulkan 1.0 submission?
Yeah, so Vulkan, we are already conformant for Vulkan 1.0. This happened like almost a year ago. And what we are now getting ready is for Vulkan 1.1. And I hope we can do this before the end of the year, hopefully very soon.
Does the Raspberry Pi have a tiling GPU? If so, have you looked at some of the experimentation Fredrino had on maximizing the length of each render pass?
Right. So yes, it's a tiling GPU, and no, I haven't looked at that yet. But I guess we will be interested in that. I mean, we know there are some things that we can do. For example, our driver can merge subpasses in some cases where basically the application is not being smart and it's splitting things in subpasses that it shouldn't do. But other than that, we are not very good at that. We also have a suboptimal optimization of input attachments where we could do better. But yeah, I would be interested in looking more into what Fredrino did.
One more from Bas. Nice to see GFX Reconstruct being useful for testing. Has it also been useful for performance testing?
Actually, we used it for performance testing specifically. So we had this problem where some of these Unreal Engine demos, they would either spawn the camera at different locations every time, or at different points in time, they would just have different performance behaviors without, probably due to the game code, not our code. So we use GFX Reconstruct to make sure that we could test the patch against the exact same GPU workload. And it was very useful for that, yeah.
Fire asks, do you have any good profiling tools for people optimizing their games or programs on the Raspberry Pi?
No. I mean, we have to optimize the CPU side code. We just use, your choice of CPU profiler. There's nothing specific for the Raspberry Pi. And for the case of optimizing on the GPU, there is a bunch of things that we may use, but like we can dump shader code and things like that. But there's nothing specific that is particularly useful in this regard. I guess a combination of GFX reconstruct, render doc, CPU profilers, and things like that is all that we have. I would love to see better tools, but for the time being, that's what we have.
Okay, it looks like that's all from the audience. Thank you very much for your talk, and well, have a good conference.
Thank you, you too.
Up next is Erika Nunes with the Lima driver status update, and it's going to happen in about 15 minutes. See you then. And we are ready to go with the second talk of the day. Enrique Nunes is going to present the latest on the Lima driver. Enrique Nunes, please take it away.
Hello everyone, my name is Enrique Nunes. I'm one of the developers working on the Lima graphics driver, and I'm going to present the Lima driver status update 2021. The last time we did a presentation about Lima was about 2 years ago in XDC 2019, but back then the driver was still not fully functional. We were still working on some basic functionality, and a lot has changed since then. There have been many improvements to Lima, which is why I wanted to bring this new status update. So the presentation starts with an overview about Lima and then a recap about Mali 400. Then I have the status update where I went back to see what were some of the more relevant work that happened since our last presentation. Then I go over a benchmark, which I think has some interesting results. And then I would like to open a discussion about how do we go forward from this point. So Lima is an open source graphics driver for the Mali 400 series of GPUs from ARM. It's done via reverse engineering. The Lima project has actually started a long time ago, and there's a lot of history. And I'm not going to go over all of that history again here. We did go over this in our previous presentation. So when I'm talking about Lima here, I'm talking about the version that exists in upstream today in Mesa since 19.1 and the Linux kernel since the kernel 5.2. And Lima today exists as a fairly standard open source driver. In Mesa, it uses the Gallium infrastructure, the Near infrastructure for the compilers. In the Linux kernel, it's a standard DRM driver. So it's a pretty standard open source driver like all of the other ones that exist today. It is a fully community developed driver, which means that everyone that's working on it is working as part of the community, and there are no, as far as I know, developers who are full-time employed or dedicated to working on Lima. And I think it's important to keep this in mind because it has implications on, for example, how much time or effort we have to invest in this. These are a little bit of stats about the GPU itself, not necessarily all about Lima. So the original Mali 400 GPU came out in 2008. There were earlier models that came before that that are related to it, but I'm not going to consider here, just considering from the Mali 400 what came after that. Then there's the Mali 450, which is mostly similar, but that there are some differences, especially in submitting jobs to the hardware, but it's pretty similar. And then there's the Mali 470, which is newer, but much less popular than the other two. In fact, there hasn't been a lot of interest in it recently. It's not even supported by Lima at this point, just because nobody really seems to care much about it. ARM claims it to be one of their world's most shipped mobile GPUs, and I believe at some point in the past decade that was the most shipped mobile GPU. And you can still find it today in some single board computers, maybe some lower end tablets, set-top boxes, or these types of devices. It targets mostly OpenGL ES2. That's what the binary driver from ARM supports, also OpenGL ES 1.1, but no desktop OpenGL support unless you do some sort of compatibility layer on top, which we do get in Lima because of the Mesa layer that allows us to expose desktop OpenGL. The GPU is a tiling rendering model, which is pretty common in other mobile or embedded types of GPUs, not only the Mali series of GPUs. This is important to keep in mind if you're targeting applications for the Mali GPU, because there are some things you should not do that could affect the performance of your application on a tiling rendering model. There are also some things that you can do to exploit this model to improve performance and reduce power consumption. So it's something to keep in mind when targeting an application to this type of GPU. The GPU does not have a unified shader architecture, which means we have different architectures for the vertex shader and for the fragment shader. This shows a little bit of the age of the GPU because pretty much everything that came after this generation came with a unified shader architecture, which means you only have one core that can do both vertex shader and fragment shader, for example. In the case of driver, this has a serious implication because it means we need to maintain two different compilers, one for the vertex shader cores and one for the fragment shader cores. So that's we have to maintain two compilers. And the hardware may come in different configurations with up to 8 fragment shader cores and up to 2 vertex shader cores. So this will depend on the implementation from the SoC vendor. The cores, they do not support integers, although you can use integers in your shader using the OpenGL shading language. The only thing that's supported by the GPU is floating point 16-bit, so everything has to be lowered down to floating point 16-bit. Even if you use the qualifiers from OpenGL shading language like high precision or low precision, that will mostly be ignored because the only thing that's supported by the hardware is floating point 16-bit. And finally, I include this last one because there is often still someone confused about it, but the Mali 400 is a GPU in the sense that it's a 3D accelerator, but it's not a display controller. Every SoC vendor will include a separate display controller or display engine that will depend on the vendor. And that is the thing that will be driving the screen, like an HDMI screen or LCD display. To be able to show the images that are rendered on the GPU on a screen, there needs to be a communication between the hardware and there needs to be communication between the drivers. But the Mali GPU itself is not putting the images on the screen. This is something to keep in mind when debugging, especially basic enablement of the GPU or some newer board. So one thing I wanted to discuss a little bit is this question: is it still relevant today? Because someone might make the point, and I think it can be a valid point. The GPU is over 10 years old, so is it still worth it to spend time enabling it and improving it, or is it just trying to enable some legacy or obsolete hardware? So why are people still working on this? So from my perspective, it can still be relevant today, at least in some niche applications, which is what I wanted to showcase here a little bit. The first one, in case you haven't heard, this device. It's called the PinePhone, and it's a device that started, it's a smartphone that started shipping around last year, and it is a Linux phone. Well, it runs Linux, of course. In fact, it runs mainline Linux, but it's different than most other phones in the sense that you can run regular Linux distributions on it. So basically, every distribution that exists for the PC or laptop space has been ported to the PinePhone, and you can run an operating system on your phone that will be running, for example, a Wayland compositor, and you can run normal Linux applications on it. Which is pretty cool. And yeah, you can choose which distribution you want to flash on it. For example, there's Manjaro, which I believe is the default one. There's UBports, which is something that derives from Ubuntu. There's KDE Neon. There are other mobile operating systems like Postmarket OS, which has been ported to the PinePhone. There's also an Android port for the PinePhone. And I think the fact that the PinePhone exists is pretty cool because it greatly increases the number of people who are using Lima today. The other application that I like to showcase are these media center or media player types of applications. We did get a lot of involvement from people who are enabling operating systems for this, for example, on IRC. I think it's an application where the Mali 400 can still be relevant because most of the work is not being done by the GPU anyway. The GPU is basically compositing video frames that have been decoded by another piece of hardware, which would be the hardware video decoder on the board. So we don't really need a very powerful GPU to do this. So many of these cheaper single board computers that come with the Mali 450 could still be used for this type of application. And these two applications, the people who are working on it have reached out to us a lot, for example, filing GitLab issues that helped us identify problems with the driver or an IRC. So I think these are some spaces where there's still interest in using the Mali 400 series of GPUs. So now onto the status update itself. This is where I went over our Git history and tried to find some of the most notable work that has happened in the past couple of years. Some of it has existed for quite a long time, but I put it in here anyway because it was never mentioned. The first one is the job submission rework. Which was pretty important work for Lima. So before that, we basically only had single queue for a job. So if you would do a frame buffer switch, we would always have to flush all of the work that has been queued there. So after this, now we have multiple queues, so the driver performs much better in situations where you have to switch frame buffers all the time. There has been also enablement, for example, on partial update and frame buffer invalidation extensions, which are pretty important for the tiling rendering model, like I mentioned before. So all of this is supported in Lima. There has been work on some caches. The first one is a cache for buffer objects that has also been there for a long time now, so that you don't have to go to the kernel to allocate buffer objects all the time. There have been shader caches. We actually have two of them now. The first one is the runtime cache, because there are some OpenGL things that you can do that will require shader to be recompiled. One example is that to do the final compilation for the shader, you need to know what are the formats for textures that are currently bound. So if you keep switching that all the time, before we had the runtime shader cache, there would be a risk that the shaders would be recompiled on every frame, and of course that would be pretty bad. So we have a runtime shader cache, and later on there was also, with the PinePhone, people enabling some very early versions of GTK4 hit a case where some of the shaders were extremely big, and they would compiling all of them was taking something in the order of a few seconds every time you would launch an application, and of course that's not really great. So we did some improvement in compiler compilation time, but there is also a disk cache. So now you can save these compiled shaders to the disk and just load them from the cache. There has been a lot of compiler work since then. In fact, by the time we did our previous presentation, the shader compilers were not even complete. You could not do things like complicated control flow, and this has been supported for a long time now for both the fragment shader compiler as well as the vertex shader compiler. So I would say it's not even only complete, but there has also been a lot of work in optimizing. For example, on the fragment shader, one of the things that can be done to optimize for performance is to combine multiple instructions into a single one. And there's a step in compilation that does this, and we improved this a lot, so more things can get combined now. There is still work that can be done to improving this, like I will mention later. But the situation today with the compilers, I would say it is very stable. We don't have many known very big problems with the compilers. It has been stable for quite a long time already. So the compilers are in a good state. There have been lots of bugs fixed. Many of these come from the applications that I mentioned in the relevant applications before. I just collected here a few of them, which were the more interesting visual types of glitches. Of course, all of this has been fixed, but going here from left to right, the first one are some GTK applications that stopped rendering fonts, and this happened because we enabled support for RG textures. And then something in Glamour stopped working because we had RG textures, but we didn't support texture swizzling, and that was a little bit tricky to figure out. But it's fixed now. The other one, the half GLX gears image, was Glamour HUD. So this never worked, but for some reason nobody reported it before. There were a few problems with the shaders that are used for Gallium HUD. It's fixed now. Then at the bottom there is this test image that was from when I was doing some work trying to enable, trying to fix some of the cases for the video decoding applications. I was trying this Vivid test driver, which is a video for Linux test driver. And the application just showed me that window. There was a shader problem that for some reason was also not caught by any other application. So that's also fixed. Then there are a bunch of icons. I believe this is something from UB ports after some of our shader work. And this was actually pretty nice because we were doing this series of patches to improve the fragment shader compiler. And then on the next day, somebody already found some of these issues that came from that patch set. So people were really trying the latest version every time, which was pretty cool. Then we have the jellyfish. It should not be red like that. There was actually a series of problems in trying to do video decoding. In this case, it was related to YUV textures again, like the other one from the Vivid driver. I think those fixes were pretty important because they enabled, they fixed many problems that were on the media center types of applications, and using, for example, imported buffers and imported RG textures to do some video decoding. And yeah, that's I think that was a pretty important fix. And then, of course, people wanted to run Super Mario on the Pine phone, and that was terribly not working. There was this a pretty bad bug with reusing buffers that contain vertex data. Well, of course, that's also fixed now, but it was cool that people were trying to do that, and they reported it very quickly after that port came out. Other than that, there has been some work in documentation. In fact, this is something that changed in Mesa. There was this documentation rework, I believe, a couple of years ago, and there is this space where there can be driver documentation. So we had for quite some time now some external documentation for Lima. What I did was basically to port that to this new format, and I also wrote this FAQ because, well, many times people were coming to IRC and ask the exact same questions. For example, when are you going to support OpenGL 3, which is something that we cannot because the hardware has serious limitations for that. So at least now we have somewhere to point people when they come up with those same questions. And I think it looks pretty nice now, together with the other drivers. I think it makes the driver feel a little bit more official inside the set of Mesa drivers. Then we have CI for Lima. So we actually had CI for the first time over a year ago. People from Collabra and Bay Libre were working on it, and it existed for some time. But then after some point, I don't know exactly what happened. Maybe the hardware stopped working, or people didn't have enough time to spend on it anymore. But it was disabled and basically never enabled again. And I had this set of boards that I had the idea to enable a CI pipeline for Lima on it. It turns out it's quite challenging to enable hardware. I know there's a later presentation on this XDC on this topic, but it is actually a lot of work to enable hardware to work with the CI that we have today in Mesa. CI that we have in Mesa is great, but for example, I had to learn about Lava itself, about how to create and maintain an instance for it. The boards, of course, have to be in a reliable state. They have to use NFS. They have to be power controlled. They have to have a serial port that is accessible by the Lava instance. So, well, another thing is that while they're running code from the internet, so if I'm going to allow the boards to do that, they should at least be on a separate network that doesn't have access to the rest of my computers. So there was a lot of work, but it's officially enabled today again. It's already running jobs. I'm actually a little bit surprised by how many jobs it's running. I was expecting it would not be running many jobs, but it turns out there are maybe 10 to 15 jobs that run on it per day at this point. For example, from work that is happening on shared code like in Near or in Gallium. So it's pretty cool. I think the boards are getting some great use there, and it's a great feeling that now people can work on the shared infrastructure and not affect Lima. We did have a patch that was submitted to Lima before, but the submitter was not very sure because it didn't have hardware to test. So now this should not be a problem anymore. And if you're curious how the Lima CI board farm looks like, it's this stack of boards. I think the cases are pretty cool the way that you can stack them. They are turned off most of the time. They're not running jobs. It also looks a little bit more messy than this now because I had to add the serial connections. 3 of them are used as runners, and the last one I used as a control board because you need to have the serial ports. These boards usually have the serial connectors on the GPIOs, so we need to have a lot of USB ports and to make the serial accessible on the network, for example. So this is what it looks like. In case anyone else from the Mesa community wants to enable something like that and would like some opinions, I don't know if there are other Lava instances that are not backed by a company or something. In my case, I just have my individual Lava instance. If somebody is interested in hearing more about that or my experience, please just reach out on IRC. Another thing I wanted to bring for the status update is our the AQP results. So the AQP is the OpenGL yes conformance test from Kronos. We are currently targeting the OpenGL ES2 conformance test. And it's cool that now I don't even have to run it on my own boards anymore like I was doing in the past. I can just copy the results from the latest CI job and show it here. So we are passing almost 16,000 tests. There are 59 that are still failing as expected. There are some warns, some skips because it's not supported by the hardware, and it doesn't take a lot of time to run that. The expected fails, at least the last time I looked more in depth into that, seem to be most of them seem to be related to precision issues. So, for example, it's doing a texture sample, but one of the pixels comes wrong because, I don't know, it's doing some math on texture coordinates and it's falling back to the lower precision. So none of them seem to be some critical problem that we should treat right away. We did do a lot of work on this over the past couple of years, so these ones that are remaining, they don't seem to be some urgent issue that we need to fix. I should also note here that the binary drivers from ARM also have some of these expected fails. In fact, there are some of those sets that are fixed in Lima. Some of them fail in Lima, but don't fail on the binary driver. There is small delta there. Maybe that's something we could look at. But at this point, I believe the results are pretty good. Another thing I wanted to mention in here is the situation with Android. I noticed that there have been great community efforts to enable Android and on devices that have the Mali 400 GPU. People come out on IRC or on GitLab issues as well. This is actually a picture of my PinePhone running the GlowDroid distribution, which is called GlowDroid. And I tried it recently, and I was actually really surprised by how smooth it feels considering all of the limitations of the hardware. This is, I believe, the latest Android version that has been ported to it, and it felt really smooth. I tried installing a bunch of applications and games and some benchmarks, and it actually felt much better than what I expected. And it seems to be in good shape. It seems that the people who are doing great work, the people who are trying to enable this. Then finally, there is the kernel side. In fact, the kernel side hasn't changed a lot in the past couple of years. One notable feature that I looked back in the history was the runtime power management, which is enabled today and it works. It's pretty cool. But other than that, most of the patches seem to be about reworks. People are changing something on the shared DRM infrastructure, and then they go and do some cleanups on Lima as well. Well, the kernel side has been pretty stable. Then I have the benchmark, and the reason that initially motivated me to do this is because I found some feedback on the internet. Maybe I should not go and look at things like that, but I found some feedback that people were like saying, well, I had this Android phone 10 years ago and it performed great. How come I have my PinePhone now with this Linux desktop stack and it doesn't feel as smooth? The performance should be at least twice as what it is as what I'm seeing. And of course, the only reason why this might be happening must be because of the graphics driver. So the graphics driver should have some problem that is lower performance to half of what it should be. This is the kind of performance. This is the kind of feedback you find if you go look in the right or the wrong places. And so I was wondering how exactly are we doing, because nobody ever showed some numbers or some benchmark like this before. So when I started doing it, I realized that it's actually not so easy. Maybe that's why people didn't do it before, because it's hard to find a platform where you can run both the binary driver from ARM as well as Lima, because most of the images for any available boards that you will find will have a kernel like a 3-point-something kernel that is really, really old, and Lima was available since the kernel 5.2. if you find images that are with something with a newer kernel, then it will have lemma. It will not have the Mali driver anymore. The only thing that I found, or the best thing that I found, was the image for the same boards that I have in CI. It's a Debian 10 image that has the Mali driver working. I tried to make the Mali driver work with other drivers, but I completely failed at that. So I just had to use an image that already has the Mali driver working. And then I was able to use the vendor kernel that they have for it that has lemma, and then I could just delete lemma from one image and delete the Mali driver from the other image. So I had two images on the same board. I could do the benchmark. And I also included in here a Raspberry Pi 3 with the same benchmark. The main reason I'm including it in here is I'm definitely not interested in doing a performance contest or comparison or anything. I just wanted to have a reference of another Mesa driver just to see if there would be something off with the numbers, if that would be something that is because of Mesa or because of lemma itself. So it's useful to have another driver, and the Raspberry Pi 3 is kind of the same class or generation of GPUs. Then I did an application which has to be OpenGL ES2 because that's the only thing natively supported by the binary driver. So I just used the GL Mark II benchmark. And yeah, like I said, I'm really not interested in doing a performance contest. I don't want to claim one driver is better than the other or anything like that. What I'm mostly interested here is to see if we missed some important performance optimization, or if we happen to have some fundamental problem with lemma that is affecting performance in general. So that's the main reason I'm doing this. And I'm saying this because I don't want to see an article published somewhere saying that I'm claiming that the driver is X times faster or slower than the other. That's really not my objective here. And also, this is just GL Mark II. These are mostly synthetic benchmarks. If you really want to evaluate if lemma is affecting the performance of your application, you should do a benchmark with that application. These numbers are just representative for this particular program. So this is the first chart. These are the results for the standard set of benchmarks at 800 by 600 resolution. The first ones I want to comment are the top ones, where it was actually good to see that lemma actually is performing quite well there. You even have high performance using lemma. Of course, these are the simplest ones. They are some fairly simple geometry and some fairly trivial shaders there, but it was cool to see that. I think this already provides an original idea that we probably don't have any sort of fundamental performance problem with lemma. I want to comment on some of the other ones, but I'm going to jump to the full HD results. The first one I wanted to comment is this shadow benchmark, which is a little bit of an outlier. And I went to look into this, and it turns out it's because we didn't support 16-bit depth buffers, and it's something that the Mali driver supports. It was actually not completely trivial to enable it. It's not just listing the format in there. I had to go back to reverse engineering a little bit and figure out there's a separate bit that needs to be enabled for 16-bit depth buffers to work. After enabling that, there was still another problem, which is that the benchmark itself doesn't specify what kind of precision it wants for the depth buffers. So OpenGL will allow the implementation to choose, and the Mali driver will choose the 16-bit depth buffer, whereas in Mesa, we are defaulting to the 24-bit depth buffer. So even after that, the application will still have an impact on the final performance. If I go and change the benchmark to use 16-bit depth buffer, then I could get a closer result. So that was cool to see. Then the effect 2D-2 was really, really interesting. Some time ago, we enabled support for some different texture formats that required us to modify the shaders. And then we're using a helper function from Mesa, which will provide the swizzles that are expected that you have to apply to the result of the texture sample. It turns out that this benchmark is doing 15 texture samples from an RGB texture, not RGBA, which means, well, and what comes from this helper function from Mesa is that we force the alpha field to be 1. And this might seem harmless, we're just forcing constant 1 there to the alpha field, but it turns out that in this case it had a pretty big impact. When you do that, you're changing the result register not to be an SSA anymore. It becomes a register that can be written multiple times. And this makes it miss a lot of optimizations that could happen later on. And it actually ends up doubling the size of the shader. So that's why there is such a big performance difference in there. And this is something that we still need to work on. Of course, it's exaggerated here because this is doing basically only texture samples. But it was an interesting thing to find out from this benchmark. And then the last one I want to comment is loop-3. The difference between the first 2 loop benchmarks and loop-3 is that loop-3 it comes from a uniform, and for some reason, the reason this one in particular is interesting is that both the VC4 driver and Lima seem to do a much worse job at this particular benchmark. And I wanted to see why. At first, I thought it's because we are loading the uniform value at every iteration of the loop. That doesn't seem to be the case. I thought the Mali driver was somehow figuring out the bounds of the loop and rolling it, but it also doesn't seem to be the case. Although the shader in the Mali driver for this benchmark is much more optimized. I'm still not sure what's the case for this one, but I think we should look into that. Yeah, so going back here, there are many other ones that we could take a look at. I wanted to know here which ones of these benchmarks are ones that are affected only because of the shader size, which I believe is the explanation for many of these. But if there are some of these where the shader size does not seem to be the thing that is causing a lower frame rate, then I would be interested in knowing what's the reason for that. So I came out with this other chart, which compares, I removed a lot of the shaders in here because they were not very interesting. They were very similar results. And I wanted to see here which ones are the ones that have the worst or the biggest difference in the shader instruction size, and compare that with the previous results to identify if there is any other of those other benchmarks that is being impacted for some other reason. So if we look here, for example, effect 2D-2 has a pretty big difference, and that's one that I went to look into, and then I found out about the texture swizzling thing. There's probably more data that we can obtain from these charts, but that's still work to be done. So going forward from here, one of the things that we have today is that there are not many issues in GitLab, and I don't know what to take from this information. Maybe there are no bugs left, and maybe everyone's happy, or maybe people are not reporting the issues, or I don't know exactly what's the reason here. So there's not much recorded backlog on what to do. We could do more performance work. For example, based on the benchmark that I showed before, we could do more work on improving the compilers, maybe some general improvements. I do have a series of patches that enable hardware performance counters. It's just not merged yet because it has some impact on the kernel ABI, which doesn't have space currently, and you have to change that. Doesn't have space for the performance counters. So that's something you still need to evaluate, but there also didn't seem to be much interest in that. So what I believe at this point is that we would really need more community feedback, more issues being filed if people are still hitting any issues. Otherwise, we will just work on random things that may not affect. And then going back to the applications that still make the GPU relevant, maybe you should work on that, but it would be great if people would continue to report if there are still any issues that they have in particular with those applications. And this is the end of my presentation. Here are some links to the documentation, our mailing list, and our IRC channel on OFTC. There are always people on the channel. There are people on different time zones, but if you stay there for long enough, someone will reply to you. So thank you for watching. Hope you enjoy the rest of the conference.
Okay, thank you very much, Eric Nunes, for the talk. And now we can get to the QA session. So, are there any questions from IRC? HeyDKR asks, how much testing has been done on the GL applications, either through native GL or GL for ES?
Honestly, I don't know that. I believe many applications are still using the same builds that are used for desktop, so they could just be using the GL side. I don't know if anyone, I think nobody's using GL for ES because you do have both GL and GLES from the Mesa compatibility layer. But I don't have data on how many people use GL or GLES specifically.
Okay, and it looks like that's it for questions for this talk then. Thank you very much for the talk again, and have a great conference.
Thank you. Thank you for watching.
Okay, and we're ready to go with the next talk of the day. Alyssa Rosenzweig is going to present us the Occult and the Apple GPU. Alyssa, the stage is yours.
Hello, and welcome to this magical talk in the magical world of Toronto, Canada. It's not really that magical. We have construction, though. And this is the talk on the Occult and Apple GPU. I'm Alyssa Rosenzweig, your resident witch, and we'll be going on a magical adventure. Ooh. For some introduction, let's meet the wizards we'll see on the way. There are 4 of them, not just one when you follow the yellow brick road. That would be Dougal Johnson, who reverse engineered most of the instructions that we'll be talking about today. Hector Martin, who's been spearheading the whole Linux on M1 project. Sven Peter, who is our resident kernel hacker, and myself. As is tradition for any fruit-related device, there is the disclaimer that this was designed by Asahi in Canada and was assembled by cheap labor in, also Canada. That was me. I don't get paid for this. Fine. To start off, I would like to talk about the DCP. Today we'll be talking about the graphics stack on the Apple M1. And like any ARM system, there is the display processor, which is responsible for HDMI, and the GPU, which is responsible for the 3D rendering. And these are 2 unrelated blocks of proprietary Apple hardware. We'll be talking about both today. So first, I would like to talk about the DCP, which is responsible for the display side. The DCP is the acronym based on our best guess, based on the behavior of it. It stands for Diabolical Cluster Puck. Wait, that can't be right. This is the display coprocessor. It manages the display controller. It is not the display controller. That's a key distinction. It is a coprocessor that has its own coprocessor. It's coprocessors all the way down. There are 7 megabytes of firmware on this thing. Linux or Mac OS does not talk to the display controller itself. Those registers are just not even in the device tree. There's this massive pile of firmware with its own pile of firmware that does all of the display controller interaction. And we just have a API to deal with in the kernel space. Yeah, I don't know either. Like, what is happening here? The DCP runs the RT-Kit operating system. This is the real-time kit. It is Apple's secret real-time operating system that is running on every piece of firmware, or not every, with the exception of the Secure Enclave, which has its own Secure Enclave operating system. It's running on essentially all of the coprocessors on Apple devices. It's also running on things like the AirPods. It's a fairly large operating system, not by Linux or Mac OS standards, but by the sorts of things you'd run on a firmware with real-time constraints. I mean, it's a whole system. And for our purposes, we're not interested in RT-Kit per se. We're just interested in interfacing with it. And all of the RT-Kit processors have a standard interface over shared memory, because this is a system on chip, which means we have that shared memory, which is very high performance. And there is a physical mailbox, which is symmetric between the application processor running Linux and the coprocessor running RT-Kit. And this just lets them send about 64 bits of data per message, which means you're not actually sending commands for the DCP in this case over the mailbox. You're just sending a command with essentially a pointer to shared memory to look up the actual command, which could be several kilobytes in some cases. Again, why we don't, I'm here to explain what Apple has done in their design. I am not here to explain why anybody thought these were good design choices. At any rate, the DCP is worse than just any old RT-Kit firmware. The other RT-Kit firmwares, they are at least on a very well-defined interface. The system management controller, for example, it has a very simple interface based on key values and some interrupts and that sorts of things. It makes sense. The kernel driver for it it doesn't make sense, but by Apple standards, it makes sense. The DCP, on the other hand, the firmware is a massive pile of object-oriented C++ code, not C code, And the whole thing is just based on arbitrary remote procedure calls. There's not a defined ABI between the application processor and the DCP. You're just making calls across one processor to the next processor. It's worse because the calls that you make, you might need to make other calls to respond to them, and the DCP might need to make more calls to respond back and forth. And so in effect, you have a call stack that crosses across multiple coprocessors, all on a completely unstable ABI. So every single time macOS updates and there's a kernel update with a firmware update, the entire ABI changes. All of the enumeration of calls is completely different, which means we can't even just pin one version of the firmware because there will be changes in the future. We're just stuck trying to deal with all of these different pieces of slightly different firmware at the same time and being denied access to hardware. And I can't even complain because apparently this is the status quo for macOS now, because macOS is doing the same exact interface we are. The only benefit that macOS gets that we don't is that they can pin a specific version of firmware for every kernel because they're able to distribute a single kernel image bundled with the firmware. We don't have that luxury since we need to be able to support different distribution kernels with a given piece of macOS firmware on the DCP. And so you might ask, where did this massive pile, 7 megabytes of C++ firmware come from? While we haven't done too much forensics on it, the most likely scenario would seem to be that they just took their old iPhone display driver, split it in half like it's a sandwich, and then stuck one half on the application processor and stuck the other half on the DCP and called that a design. Why this is desirable? Again, my magic only goes so far. How does this look in Linux? Well, it's very goofy. We're still going to expose a basic DRM driver the same way any other display controller would work. It's still a KMS driver. We're still supporting the full Atomic API, but it's really goofy looking. Usually, the display drivers are taking in the changes in the graphic state from DRM and then setting registers to actualize it on the hardware. And then there's a ton of work to pipe the interrupts through for VBlank and so forth, hot plug. And it's, hardware drivers. We don't get that luxury. We're just doing remote procedure calls all the way down. And by the way, we're writing it in C code, not C++, despite the fact that we're interacting with a C++ API that has classes and objects as just part of the definition of the API, which is, the driver is haunted by the ghosts of IO Surface and IO-Kit and all of these Appleisms, which really belong in the space of macOS and which we really would like to keep in the space of macOS, except for the fact that, well, we don't have that choice. Oh, well. So, again, what is happening here? I mean, taking a step back, taking some of the emotion out of it for a little bit. Yes, it's goofy looking. Yes, I'm a little scared of the maintenance burden, but it's actually not very much code relative to other display drivers. And I mean, it works. I'm giving this talk from Linux on my M1 device right now. Okay, that's half true. The camera is on my phone, but the slides are all being presented from GNOME at 4K 60 on my M1 Mini, and the audio is going over USB headphones. And I mean, it's entirely possible that I'm just speaking to myself because the whole setup has collapsed. But if you are hearing this, the drivers work. I hope you're hearing this. So that's all I want to say about the diabolical cluster puck for now. I mean, the display coprocessor for now. And with that, I'd like to turn our attention to the other half of the Apple graphics stack on the M1, and that is the AGX. This is most likely the Apple Graphics or Apple Graphic Accelerator. The fact that it's called AGX does not bode well for those of you who are still haunted by PowerVR, which has SGX and RGX. Actually, I'll do you one worse. In the Apple device tree, the node for the AGX GPU is labeled SGX. I don't even want to think about the implications of how that came about. At any rate, the AGX is the Apple GPU. It is like its PowerVR predecessor, a tiler. The instruction set is very modern, very forward-thinking. It's purely scalar, not this half-scalar, half-vector dance that a lot of, for example, the modern Mali GPUs do and the AMD GPUs do. This is just scalar all the way down. There's no silliness around SIMD like the Intel instruction set. All in all, it's actually a really lovely instruction set to program for. And it was a lot of fun bringing up a compiler for it. Even the scheduling model, from what we can tell, seems very sane, since it's the details of the internal pipeline don't get exposed to the compiler. So if you just write code like you would write assembly by hand, that will be functionally accurate in every case we're aware of. The only scheduling-like work that is functionally required is just dependency weights and scoreboard sporting for textures and memory loads. That said, it does appear that the hardware is dual issue or maybe multi-issue or something along those lines. So there is a performance benefit to reordering instructions to group them in certain ways. And so you will see the Apple compiler reordering a little bit. For the most part, I'm not worried about scheduling for this hardware in the same way I would be for just about every other GPU out there. So after I guess nice instruction set, evil display coprocessor, I guess that averages out to a just average level of insanity in your graphics stack, because everybody has something insane in their graphics stack. Don't even get me started on the Rockchip one. The other key point that I'd like to emphasize about the Apple GPU is that Apple has their own graphics rendering API, Metal. There is no support for Vulkan except partial support via a third-party Molten Vulkan. There is very limited support for OpenGL and OpenGLES. I have not seen a conformance submission for either in years from Apple, and even when things are functional there, it's not clear that it would be using the hardware in an optimal way, simply because it's not the priority. And the bottom line is that this is a part made for Metal. It has all the features needed to efficiently implement Metal. It does not have all the features necessary to implement OpenGL. And we'll see the implication of that in a second, because we do support AGX and Mesa now. The initial code for this landed in April of 2021. It's seen active in-tree development since then, and it's a totally standard OpenGL driver in Mesa, using the Gallium 3D infrastructure for the driver, totally normal stuff. It's just a command stream. There's really, I was going to present about it, but there's really nothing special here. It's a Gallium driver. What am I supposed to say? And there's a NUR compiler, which, again, totally standard. NUR is a joy to work with. Huge kudos to Jason and friends for making a immediate representation that's totally lovely. And it compiles to the hardware, which, again, the instruction set is lovely. So we're all good. We have our OpenGL driver, right? Well, we're still reverse engineering this thing, and Metal lacks key OpenGL features, which means that when we hit one of these features, we have just a few options. We could be 1, non-conformant, not an option. So we'll call that option 0. So 0, non-conformant. 1, we could just emulate it in some highly inefficient way in some cases, or just a mildly inefficient way. And we have to do this in a couple cases. We could, 2, try to reverse engineer what little OpenGL support is present in macOS, but this is non-trivial since the GL environment there is frankly harder to work with than the one on Android. And if any of you have had to reverse engineer on Android before, that should paint a picture. Or 3, well, 4, but 3 if we're counting from 0, just try to guess our way through. And that does work, right? I was able to guess the magic numbers. Ooh, magic! For drawing quads, for example. That was fine. But it's not a not a fun time, because again, part made for metal. We're not supporting metal on Linux. We're supporting GL and eventually Vulkan. There's a huge impedance mismatch there. The one thing that we have to our benefit is that metal in many ways is close to Vulkan in its capabilities, which means most of the problems we're facing have already been faced by the Zinc driver. And in other cases, a lot of the stuff removed in hardware from AGX was already removed from the AMD hardware, which means you have Radeon SI and ACO as your cheat sheet on how to handle those. So it's frustrating, a little annoying, but not anywhere near the league of the DCP, so I best should not complain, because the AGX all in all is a nice GPU. So it's natural that we have some fun with AGX. Let's talk about divergence. There are lots of ways to handle divergence in hardware. There is the divergence in graphics hardware. The non-way is to just do no warping whatsoever, just like a CPU, and then there's no problem. However, modern GPU designs want to execute multiple threads at the same time. At minimum, have 4 threads together, usually 8, 16, maybe even up to 64 in the case of AMD. And the problem with doing this is that if one thread tries to branch in one direction and the other thread branches another direction, for example, if you have an if statement, then which one do you execute? Well, you have to execute both and turn off some threads at some point, turn off the other half at the other point, and try to reconcile that. And so there are different strategies on how to handle divergence. The easiest to work with, the compiler, is what Mali does, where it gives you the same exact interface you would have on a CPU. You have conditional branches, you just write the code like you would write x86 assembly or ARM assembly, and there is a dedicated piece of hardware which handles reconvergence, that is, determines when threads need to be enabled and disabled. And aside from some basic hinting about the control flow graph that the compiler has to give, it's very simple to compile for. So that's one end of the spectrum. The complete other end of the spectrum would be what AMD does, which, to my understanding, is have the compiler manage everything itself. You have the execution masks for which threads are executing at once, and it's up to the compiler to manage that itself and do all of the analysis that Mali would be doing in hardware. That, from what I understand, is rather annoying for the ACO compiler to deal with, but again, it's clear where that would come from. Apple, on the other hand, has a, to the best of our knowledge, completely novel approach for this. Their entire handling of divergence is based around this idea that your control flow graph is nested. So when there's no divergence, there's 0 nesting. When you have if you're inside an if statement, there's 1 layer of nesting. If you have a for loop inside of an if statement, that's 2 layers of nesting, and so forth. And the whole technique is just counting the layers of nesting and working from there. Yeah, I don't know either what to make of that, but let's see how that plays out in practice. AGX has 32 threads in a warp, which is a fairly standard number for a desktop GPU. It has a execution mask, which is implicitly there, but which, unlike other GPUs, is not accessible in assembly. It has to be managed implicitly, and we'll see how you do that in a moment. It does have an explicit count of nesting in the control flow graph, and this is just a 16-bit register, a general purpose register that when you are doing control flow gets reserved for this nesting count. And then it has 2 classes of control flow instructions, we'll say. The first are jumps that are completely warp static. They apply to the entire set of 32 threads at once, which means you can't have divergence from them. And the other are structured control flow instructions. And it seems funny to talk about an if statement instruction or a while loop instruction, but that's very much how it's expressed in the AGX assembly. And these are internally, they're essentially arithmetic operations that are responsible for manipulating this nesting counter and manipulating the execution mask implicit register, which means when used correctly, it does correspond to the control flow that you're trying to do internally, but it's not always obvious how to take these primitives and map it back to, say, NIR's control flow, which is our job as a compiler. So for a recap, what do we have in NIR? Something much more simpler. There are if-else statements, there are infinite loops, and there are breaks and continues out of the infinite loops. That's it. So how do we map these? The easiest mapping we can do would be for an if statement. And because we have this if statement instruction, sort of, and the semantic here is that the hardware, when it gets this if statement instruction, will evaluate the condition, and then based on the condition, if the condition fails, it will increase the nesting count by 1, and then update the execution mask. So if you think what that means, if a thread is active going into this, and then the condition fails, it will have a nesting count of 1 now, and then it will be inactive, and then it won't execute the body of the loop. However, if there are 0 levels of nesting to become active again at the top, and the condition is true, then this if statement instruction does nothing because it's still active after, and it executes the body of the loop. And then at the end, we have to do end the if statement by popping off this 1 layer of nesting. So then the threads that are active do nothing because it saturates at 0. There's no negative levels of nesting. But the threads that are skipped the if statement currently have their thread nesting level at 1, so it pops down by 1, and now they're active again because it's down to 0. However, the point of counting nesting is that if this if statement were embedded in a larger if statement or for loop or something, there could be other threads that were already inactive going into this if statement. So by adding to the nesting count, they will not only continue to skip this if statement, they will have their levels of nesting restored at the end by the pop. And this is sort of the point of having this nesting count as opposed to manually managing the execution mask. So if you look at this assembly, it's sort of clear where this comes about, but it's also very clearly strange. But I digress. How do we extend this to if-else statements? It's just as simple. We now have an else instruction in the middle that operates just as the logical complement, in a sense, of the if statement. So it will then swap all of the threads that have thread count or nesting count 1 to the nesting count 0, making them active, and make all of the threads with count 0, so currently active, make them 1, so they're inactive, then pop at the end. Great. This makes sense. It works. It passes the tests. What about loops? This is where things get kind of tricky and kind of complicated, and it will take us a number of steps to figure out how to get this right. So our first try would just be using this jump instruction. We have this warp static jump, so we can just use that to loop through the same number of instructions over and over. And we are using, in particular, this jump if any are active jump. But so, fine, it's a loop. Not the kind of loop that NIR wants, because this is a loop for the 32 threads at once, not for just any one thread like NIR semantic. And there's no way to break out of it either. So our next thing to try is using the actual while instruction, which, again, remember, the control flow arithmetic instructions are not actually doing any control flow. They're just manipulating the execution mask and the nesting count, which means this while instruction alone would have no way to jump back. So we need both the while instruction and also the jump together, and you have them both together at the end of the loop. And so the trick that we have here is that, well, the way that this while loop instruction is working then is, in this case, it's just always, well, we'll see why we need it in a moment. The moral of the story is that we can still break out. We can now break out of this by manipulating the nesting count ourselves because it's just a register. So as a very simple example, if we are active, we have a nesting count of 0, but if we want to become inactive, we can set the nesting count to 1 and then force the execution mask to be re-updated by a sort of no operation control flow instruction. And this has the semantic then of making the thread go inactive. The other threads will continue to execute the loop, but eventually you'll get to the end, and if there are no more threads running the loop because they've all become inactive with this while and this pop and this break, then the jump execute any will not do any jump because there's no threads active anymore, and then we're done, except for the fact that all of your threads are inactive now, but details. Why don't we fix that? It would not be good to only be able to do a loop, and then once you're done with the loop, the whole execution is terminated. Likewise, if we have nested control flow, we don't want to clobber that either, which would be what would happen with our previous implementation. So in this case, we just need to push the nesting count up by 1 at the beginning and pop it down by 1 at the end, and things allegedly work out if you do it this way, allegedly. So this is a good start. It will implement an infinite loop faithfully, which is what NER needs. We can break out of the inner loop. We can even break out of multiple loops at once, but NER does not call for this. But what we can't do, and what there's no obvious way to do, is be able to do a continue in a loop. So at this point, you might be very stuck. When I was looking at the notes for this, I was stuck myself, didn't get it myself, and I was just hoping that magically a little birdie would come and whisper in my ear. And indeed, such a little birdie came named Dougal, and I will, in my ear said, quoth to Dougal, continue as a break. We can model a NER loop as a pair of loops instead, with the inner one, a pair of do-while loops, where the inner loop only runs for 1 iteration. So how do we handle this? Well, if we are trying to break out of the logical loop, that's breaking out of the outer loop. So we break out of 2 levels of nesting. If we're trying to just continue on the outer loop, then that's equivalent to just breaking out of the inner loop. And so we can implement both break and continue as break with 2 layers of nesting if we have 2 layers of nesting on the loop. And the best part about this is that the loop structure, so to speak, is implicit in the values of the nesting count. So this does not require any more instructions than would require otherwise. So we can use the same exact code we had before, but now instead of using 1 layer of nesting on each of the control flow instructions, we use 2 layers of nesting. And this gives us a completely natural way to implement both break and continue, just as different breaks. For a logical break, we break out of 2 loops. That's the so break out of the outer loop. For the logical continue, we just break out of the inner loop. And the code is symmetric in this case, setting the nesting count and then resetting the execution mask to compensate. There's only 1 little wrinkle we're missing here, and that is what happens if you try to nest this loop inside some other piece of control flow. For example, if you had the loop inside of an if statement, then when you do it this way, after you finish the loops, then everything would be enabled again after, even if that thread wasn't executing the loop to begin with because it was on the other branch of the if statement. And the solution here is very simple. It's just to reset to the appropriate level of nesting. Namely, we need to add the numbers of levels of nesting outside of the loop to figure it out. And the other trick we can use here is that NER only has 2 types of control flow. One are loops and the other are if statements. And the break only applies to the innermost loop, which means the only control flow that we're interested in counting is the number of nested if statements. And that is trivial to do with a little bookkeeping in the compiler and have working breaks and continues. And that finally will pass all of our control flow tests, and we'll be very happy because, now we have control flow on our compiler. Woohoo! Not efficient control flow, but conformant control flow. So wrapping it up, the current status for this is that we have the DCP driver functional in a downstream fork of the kernel. I'm hoping to send off the initial RFC if these patches in the next few months, but there is a lot of cleanup to do. The code is functional, but not pretty to look at. As for AGX, the code is upstream in Mesa, passing about 95% of the DQP GLES2 tests. However, that comes with the massive caveat that is passing those tests under macOS, not under Linux, because we still have to write a kernel driver for AGX to be our glue between the Mesa user space and the AGX hardware on Linux. And we're again hoping to have that in the next few months. So thank you, and happy to answer questions. And just before we go, I would like to point out, if I can figure out how to share my screen. Stop sharing screen, start, select, entire screen. I have been doing this talk from my M1 device. See, Apple Mac Mini M1 2020. So it works. I mean, works, but it works. Thank you.
Thank you very much for your talk. Now for the Q&A. Ryan Hudek asks, does pushing and popping execution masks go to memory or some hardware stack?
Right. So there's not an explicit stack to the hardware. There is a imaginary stack that the compiler gets to keep track of. The only hardware state you have is the execution mask, so 32 bits per warp, and the nesting counter, which is really a count of levels of nesting until the thread becomes active again. And this is a 16-bit general purpose register that gets tied up for control flow, and one per thread.
Okay, person 1337 asks, what are the biggest features missing from Metal relative to OpenGL? Doesn't Apple implement OpenGL ES for WebGL?
Right, so if I were to design hardware, there are a lot of features in OpenGL which I would say are stupid and which I wouldn't want to include because they're useless, slow, etc. And eventually I would cave and implement them anyways because real applications use them. And even if well-written applications don't need them, translation layers, for example, Wine would still want them. And Apple has the luxury of being able to look at the same exact sets of features and just saying, you know what, we don't need those. We're getting rid of them in hardware. So all of the, basically anything that's deprecated in OpenGL, you're not going to find hardware support for. In the M1, anything, huge amounts of the geometry pipeline are done in shaders, which is fast enough in practice. I suspect transform feedback will have to be done in software, not because I've actually tested that theory, but because why on earth would they put transform feedback hardware on a part made for Metal, and so on and so forth. So the net result is that well-written applications on Linux will run just as fast as their Metal counterparts, but there will be a lot of hoops to jump through if we ever want to become conformant and support all the random ancient legacy things and want to pass all the piglets.
Okay, NeoBrain asks, any idea how the AGX design compares to PowerVR? Have you found any similarities so far based on what little Imagination publishes?
I haven't studied what Imagination has published, and PowerVR is, of course, the last remaining GPU to not have a Mesa driver, as far as I'm aware. So I can't comment there. The high-level design is similar in that they're both tilers. They are both okay, I guess that's where the similarities end. Apple clearly designed the AGX GPU for the iPhone with the purpose of having similar performance characteristics to the existing PowerVR parts, and it was not a atomic switch. It's my understanding that there were PowerVR parts with Apple instruction sets at one point shipping on iPhones and so on, and all of that was pretty much invisible to iOS developers because the performance characteristics didn't really change. The high-level design was essentially unmodified, even though all the details got swapped out.
Okay, Radek Schwichtenberg asks, are there big differences between M1 for Mac Pro versus Mac Mini or Air? How much do you think it will be needed to support newer versions?
It's the same system on chip. M1 is M1. There are differences in binning. The MacBook Air M1 has one less GPU core than the other M1 devices, which if that's software visible at all, it will be a short amount of code in the kernel, I imagine, not something user space worries about. Then there are the hardware. The different Macs are different themselves. For example, the Mac Mini has Ethernet and USB Type-A ports, and we have drivers for that in Linux. The MacBooks don't, but the MacBooks do have a camera and will need a camera driver that the Mac Mini doesn't. So I personally have a Mac Mini. I don't have any plans to get a MacBook, so that's where my development is biased. But we're hoping that Asahi Linux will support everything eventually.
And one last question, Patrick Jacobsen asks, is the DCP firmware redistributable, or do you need something like a download script like we have for FaceTime HD, the webcam drivers?
So this is a very interesting question. I wish I touched on this earlier. It's not redistributable, but that doesn't actually matter for our case because Linux never touches this firmware. It's on a internal system partition, so it's on the internal storage, but not on the operating system partition. It's loaded by the bootloader. Presumably it's signature checked by the bootloader, and then the firmware is locked. So the operating system, be it macOS or Linux, just does not touch this firmware. This is unfortunate to us because it means we can't modify the firmware to be less ridiculous. We could not replace it with an open source version even if we wanted to. However, it neatly avoids all of the legal questions because from Linux's perspective, there's no firmware being used at all. And this is one of the great ironies of Asahi Linux to me, is that with the exception of the Wi-Fi, everything will work on Linux Libre. And this is very, very much not a Libre chip.
Okay, looks like that's it for today. Thank you very much for your great talk, Alyssa. And
Thank you for having me.
Have a great conference.
I will now magically poof out of existence.
Okay, looks like we're ready to go with the next talk of the day. That's Rob Clark with the update on Chrome OS, Freedreno, and general upstreaming. So, please welcome Rob Clark.
Hello, this is Rob Clark from the Chrome OS graphics team. I'm here to give you a bit of an update on what we've been up to with Chrome OS and Freedreno, including what we've been working on, the current status, journey so far, a little bit about our CI setup, demo, and some other useful information. So probably shouldn't come as too much of a surprise if you follow Mesa and kernel development, but we've been working on Snapdragon Chromebooks, the first two reference designs being Trogdor and Strongbad. Trogdor for clamshell, and Strongbad for detachable. And as far as I know, they're the first consumer electronics Snapdragon devices to ship with upstream kernel support. And not just that, but upstream kernel support that's in place before they even shipped. And why might you ask, do we care about upstream kernel support? Well, on the Chrome OS side of things, we need to support devices for a relatively long lifespan, which means we need to be able to do kernel updates to new kernel versions. We need to be able to do security and bug fixes, and that's not really something you can do with the Android vendor kernel approach of millions of lines of code of downstream patches. And what's more, it's, as far as I know, the first consumer electronics ARM devices to ship with open source graphics drivers, all in upstream Mesa before they shipped. And why might you ask, would we want open source graphics? Well, really, largely the same reasons as above. But also we need to be able to implement extensions and features that are important for our use cases. One recent example is the EGL-KHR mutable render buffer extension, which is important for low latency ink. Despite the awkward name, what that lets you have is front buffer rendering, essentially, which is important for low latency stylus. To reduce the latency between the pen position and pixels on the screen. And also, with an open source driver, this gives us good synergies with Intel and AMD. If you take the example of the mutable render buffer extension, that's all in shared code that's also used by Radeon SI and Iris. And there's other benefits. I mean, we found and fixed bugs that would have hit Intel or AMD when they moved to a newer Mesa. There's lots of common and shared code, NUR, threaded context, and so forth. And, you know, of course, it's also the right thing to do. So what's the current status? Currently, we're at, on the Gallium side, at GLES 3.2. We've been passing all of DQP, GLES, and EGL since maybe around August of last year, because of course that's a required part of Android CTS that we need to be passing in order to ship. On the Vulkan side, Turnip is at Vulkan 1.1. We've got maybe approximately 15 remaining CTS failures to fix up, and we're also about 7 extensions away from a 1.2. We're supporting, in addition to older generations of Adreno 200 through 500, we're supporting all 4 sub-generations of Adreno 600, where Gen 1 is 618, 615, and 630. Gen 2 is 640 and 680. Gen 3 is 650. And the most recent Gen 4 is Adreno 660 and the 7C3. And also, as of a few weeks ago, we're passing all of DQP GLES on 7C3. We also have lots of nice developer tools to, like ISASpec, which is an XML-based shader instruction set description that we use to generate the code for encoding and decoding shaders, We have a crash deck for decoding GPU core dumps, which capture the entire command stream of a faulting submit, GPU register snapshots, SQE, which is a CP processor. We capture its registers and program counters and which packet it's parsing and so on. Recently, in last year, we have Perfetto support for giving a better picture of overall system performance. So, in the beginning, I started at Google and working full-time on Freejuno in April of 2019. If you can remember back to pre-COVID days. Anholt started about a month later. Between us, we've been working on Freejuno. Anholt's also done a lot of stuff on just making Mesa better, like consolidating all the formatting enums and working towards getting rid of GLSL to TGSI and so forth. So in the first part, the focus was really finish all the big features and extensions, and start a little bit bringing down the DEQP failures. And an important part of this was getting CI set up, which is covered a little bit more in later slides. So in the early days, I think we went from maybe 90-95% DEQP pass to just having a few remaining failures by the end of the year. This is also the point where we start having a Play Store, which gives us a lot more interesting workloads and bugs to debug. I'm a big fan of SuperTuxKart, but on ARM systems, there's not a lot of games available because you're generally limited to the open source games. And this was kind of the times before crazy people started doing, emulation tricks for Steam Store on ARM. This was about the point in time where we started working on MediaMP. We knew we'd really need FP16 support to hit our performance targets. So we worked with the Gallia on retrofitting MediaMP support through GLSL and plumbing it through NUR. It was about 2 years ago at XDC when a bunch of the NUR and other developers locked themselves in a room and kind of hashed out a plan for moving forward on MediaMP. And then I think it was late October of that year that we brought up Adreno 618. This is interesting in a couple ways, partly because it's the GPU that's actually in the 7C Chromebooks that we're shipping today. But it's also the first time I think that I know of that we've done wake up with Mesa on a Snapdragon device. At this point, we would already made the decision to go with open source drivers, so there was no more blob driver available. So Qualcomm and hidden away in their labs when they're bringing up the first samples needed some way to bring up the GPU, and they did that with Mesa. And I worked remotely with them on that. So about the very end of 2019, beginning of 2020 is when we started getting our first batch of Trogdor EVTs back. This is where the so-called real work begins. This is the thing that's going to be the reference design for the Chromebooks that are shipping these days. This is where it starts getting interesting. Of course, COVID soon makes the hardware schedule interesting with factory shutdowns and parts shortages and so travel restrictions and so on. But meanwhile, we kept pushing on the bug fixes and fixing game bugs and so on, and got to a 100% DEQP and SKIA SKQP pass. And so the focus shifts more towards performance. We landed medium P support, shader compiler improvements that brought little gains, 5-10% here or there sorts of things. We figured out how to drive LRZ properly. In particular, the hardware has a nifty early LRZ, late Z mode. So LRZ is kind of like a for-free Z subsampled Z prepass that you get during the binning pass. Early LRZ, late Z mode lets you do early Z tests in cases where a later draw occludes the fragments from an earlier draw. But in a normal case, you wouldn't be able to disable early Z because, say, there's a discard in the fragment shader. This work done on plumbing UBWC bandwidth compressed buffers formats through Android, which is also used now on Intel and AMD Chromebooks, getting shader disk cache up and running for quicker game startup time, and so forth. And I'd say overall, we, in terms of benchmarks, we roughly nearly doubled the performance in the between late 2019 and mid 2020. Then the focus starts shifting more towards system performance, and it does no good if you have the best benchmarks, but if you have system level issues, CPU freak, GPU freak governor, task prioritization, so on, then you're not going to have a nice user experience. So early on, kind of counterintuitively, we had the most problems with more lightweight games. Think something like Alto's Adventure, which is not really pushing the limits in any way as far as performance, but they would just not generate enough CPU load to push onto the big cores or to ramp CPU freak up enough, and then some other thing would happen in the system and in the background, and they'd get preempted, and you'd have a frame rate stutter, and that's not very nice. I also found some issues with prioritization, in particular on the Android side of things. Surface Flinger and everything that's involved in the path from the application to the screen runs as real-time priority, which means it's running a higher priority than the work queues on the kernel side that atomic helpers use to push async, non-blocking atomic updates to the driver, which is not great. You really want that to have a higher priority than Surface Flinger starting on the next frame. So some of that has been partially solved, not the core DRM parts, but on the DRM MSM side of things, I've converted all the work queue usage to K-thread worker with real-time priorities. We still need to sort out something better for things like the atomic helpers, and that's really a cross driver issue. And that brings us up to the beginning of this year, when the first Trogdor base device, we call it Lazor. In the outside world, it's known as the Acer Spin 513 shipped. Unfortunately, very initially, we started getting reports of performance hiccups, in particular on the lower spec 4 GB devices. And so I had a bit of a crash course on ZRAM swap and Chrome OS's approach to make Chrome work on such a low memory device. It turns out the low memory devices, once you have a whole bunch of windows and tabs open, they're under constant memory pressure. So if you're kernel driver has a shrinker, you need to really make sure that that it's as lockless as possible. And in particular, count objects needs to be lockless. And you want to reduce the critical section in scan objects. Because otherwise you can be having the shrinker called on all the CPU cores at once, and that just serializes everything in the whole system, which isn't great. So I'll take part of the blame for that because I'd mostly tested on 8 GB devices because those were also the devices with larger disk sizes, and that's kind of useful when you're testing a lot of Android games to not have to be constantly uninstalling and reinstalling. But I think next time I'll remember to do some testing with mem equals 4G on the kernel command line. And we also are working on Perfetto support to improve our system level visibility, like what's going on the CPU cores in correlation to what's going on the GPU, and where are the system level bottlenecks. So here's, a screenshot can't really do it justice. You really have to play with the UI. But here's a Perfetto trace. I'm just using an Android GPU inspector as the UI for viewing the trace, but you can really drill down into very small time windows. You see on the above the GPU timeline, you see all the CPU timelines, what frequency and what tasks are running. On the GPU timeline, you can click on that surface bar there and see information about the render target, how many MRTs, what the format is, dimensions, so on. Below that, you get a broken down view of the binning pass and per tile, clear or restore, plus draw, plus resolve. And if you look below that, there's little yellow lines. If you highlight one of those, that shows you where on the CPU the command stream submission happened. And if you highlight one of those, that will draw an arrow to the point where it started executing on the GPU. And then, of course, below that, you can see GPU frequency and utilization and other performance counters. So we continued working on various CPU bottlenecks that were showing up in places. Threaded context was a big help in certain driver overhead situations. Of course, graphics bench driver overhead off screen is a notable one. We multi-threaded our shader compiler and made it asynchronous so that we don't actually have to block until you need to emit a draw with that shader. In particular, I was finding Asphalt 9 with their, which has a in-house game engine. It was generating new shaders mid-level quite a bit, which is leading to compile a new shader janks, which isn't great. The combination of the async shader compile and threaded context at least helped mitigate that a bit by hiding a bit of the latency. Another big one was user space fences and submit merging, which cut down on our number of kernel ioctls quite a bit, and helped in some cases where we're just the CPU is bottlenecking the GPU too much for the GPU to ramp up to higher frequencies. On the kernel side, there's some recent GPU dev freak rework to improve some pedantic situations, which I'll go into a little bit more on the next slide, and then DRM scheduler conversion. Which helps move blocking waiting on fences, like say you're waiting for the previous atomic update to finish. It moves that out of the user space ioctl path. There were also some cases which kind of annoyingly, we ended up having to resort to some GL vendor, GL renderer shenanigans. There were a few games that were trying to put, trying to figure out what GPU they're running on and using different tiers of graphics settings. And when they saw Mesa, they didn't understand what it was, so they put us in the lowest tier, kind of artificially restricting graphic settings and artificially limiting frame rate, which was not so great. So I ended up implementing a way to do per device GL renderer overrides with DRI-conf so that we can trick those games into actually running as fast as they should be. Oh yeah, and somewhere along the way we finished that last extension for GLES 3.2. Figured out all of the corner cases where we needed to deal with UBWC or tile demotion. So I mentioned about GPU DevFreak. What I was finding, if you look, the bottom line here is showing you the GPU frequency, and the top line, or the above that, you can see where the GPU is actually active. And you can see that we're spending time here at higher frequencies while we're not doing anything, and then spending a lot of time at lower frequencies while we are trying to get work done. And, you know, then we repeat the process. So came up with a combination of a longer sampling period to, well, this problem was especially bad on some of the games that were limiting themselves to 30 FPS because the previous sampling period for DevFreak was, I think, 10 milliseconds, which was just too short. And the constant one frame busy, one frame idle was really confusing things. So it was even worse in this screenshot here. You'd see it at a minimum frequency until almost the end of the rendering, and then it would pop up to the maximum frequency and then stay there for most of a frame doing nothing. So what I ended up doing was going with a longer sampling period to average things out over a few frames, and then clamping the frequency to the minimum when we're idle, so we're not sitting there spinning away at a high frequency doing nothing. And then to mitigate a little bit the fact that the longer sampling period would take us longer, we'd take longer to react on interactive workloads, think like scrolling a web page or something like after you've been reading for a couple minutes. There's a bit of a boost if the GPU has been idle for a while and it becomes active. We give a little bit of an extra boost to the frequency initially. So, a little bit about our CI farm. On the right here, you can see a picture of our little CI farm rack. The boards are actually kind of hard to spot. You can see some on the second shelf down from the top, and some below it. The boards actually don't take up very much space. We just stack the bare boards on top of each other with standoffs. A lot more of the space goes to the power supply, the USB relays, the network switch, and so on. So in the current state, we have about 25 runners total in the CI farm, 9 Adreno 630, although there's a couple that are offline at the moment, 8 with Adreno 530, and 8 with Adreno 307. This gives us enough to do pre-merge CI with 100% of DEQP, EGL, and GLES coverage on the Adreno 600 devices. Also a 10% coverage run with address sanitizer, 33% of a Vulkan run, in addition to several traces tests. We don't do it pre-merge, but we do nightly now, thanks to Collabora performance traces, so we can track over time performance and see if something has come in that has regressed performance. And then on Adreno 530, we've got a little bit less coverage, mostly because there's at the moment, some CPU freak issues, I believe, that are kind of limiting how much we can run. And then the 306 has 100% coverage of all the GL it can do. It's not quite enough to do Glass 3.1. And on a weekday, the CI farm's running between 500 and 1,000 jobs a day. It's much less busy on the weekends if you're looking for some CI time to test things. And because of all this, we've been able to keep the tip of tree Mesa green, and we've actually been shipping tip of tree Mesa in Chrome OS because of that. Basically, when we come time to uprev Chrome OS for Juno branch, we do a git fetch upstream main, git merge upstream main, and some testing. Do this roughly every 4 to 6 weeks, and it's worked surprisingly well. Initially, I expected that once we started shipping devices, we would switch to Mesa release branches, but this has actually worked well, so we just kind of stuck with it. We haven't had too many regressions on uprevs. Very early on, we had a couple times we hit YEV regressions, but we now have coverage of those code paths in CI. I think the only thing we hit from time to time these days are SKIA, SKQP regressions, because we don't have any coverage of that in CI, and SKIA is basically a GL fuzzer. A few of those times are actually SKIA bugs, so but you know, still catching them earlier would mean less time debugging later. And demo. Well, actually, this is kind of the demo. I, of course, wrote the slides on a 7C Chromebook running Chrome OS, and the presentation I recorded in an OBS studio running on a 7C Chromebook running Fedora and upstream kernel. So, you know, this is your demo. So, if you're curious, and I suppose everyone knows where to find upstream kernel and Mesa trees, so I didn't bother listing those, but this is what we're shipping in Chrome OS. The Chrome OS for Juno branch on Mesa is most of the time just tip of tree Mesa whenever we did the last uprev. Occasionally we cherry pick a few fixes. You know, whenever we do a merge from upstream update, the only delta is the addition of an owner's file. You know, we don't have any downstream patches. On the kernel side, the devices that are shipping right now are running a 5.4 based kernel with a lot of stuff from newer upstream backported. You know, most of the patches are either cherry picked from upstream or from a next branch, you know, from Git, and sometimes picked from list. On the DRM-MSM side, the one notable exception is we have a hack patch to tie KMS planes to a single CRTC to work around some user space issues. And for the detachable tablet devices, there's a pile of downstream MIPI camera patches, unfortunately. And then there's also some patches that are needed for the Android container to work. Android has some dependencies on some downstream patches. Other than Android apps, if you are in dev mode on one of these Chromebooks, you can just build an upstream kernel and put it on it and expect things to work. So other useful things if you're interested in playing around with things like upstream kernel and Mesa and on Chromebooks, there's this thing called SUSEQ. It's this kind of orange looking, looks like a normal USB cable, but isn't. What it is actually serial to, it gives you a TTY USB port for the kernel serial debug port, and also for the EC and CR50. So this is something I wish that Windows laptops had as well. It makes it much more less aggravating experience when you're making kernel changes and things don't boot. You can at least get a debug UART port and see what happened versus just guessing. Other things I'd recommend to have would be a USB-C hub with Ethernet and power pass-through. On all of these Chromebooks, you have 2 USB-C ports. If you're using one for the for SUSEQ, then you have one other remaining. USB thumb drive is useful to have. If you have a good image on a USB-C thumb drive, you can always recover. It's pretty much impossible to brick. And then I put here a link to Jesse Barnes has a cross-util tree on GitLab, which has scripts that make it really easy to put a kernel on one of these devices. And then we also have some docs in Mesa about replacing the Android drivers, in Chrome OS. So thank you, and hopefully by now I managed to join the streaming thing to answer questions.
Okay, that was Rob Clark with the latest update on Chrome OS and Freedreno. Now it's time for the QA session. Although it appears like we don't have any questions, so please do keep them coming.
Yeah, I've kind of been answering some questions on IRC as we went.
True. Ryan Hudek asks, how soon until UBWC 3D texture support? So I start getting a warning about it.
Yeah, that's right. I guess we do have to go back and finish that. I'd forgotten about it.
Okay, it looks like the talk was pretty exhaustive, so there are no more questions for today. Thank you and your magnificent beer for the great talk. Thank you.
Right, I'm gonna get some coffee.
Have a good morning and have a great conference. Hello there! Well, halfway through the day, and right now we have the next talk of the day, which is the SSA-based register allocation for GPU architectures, presented by Connor Abbott and Daniel Sherman. Connor, Daniel, the stage is yours.
Okay. Hello, and welcome to our talk about SSA-based register allocation for GPU architectures. With me is Connor. He's the creator of the IR3 register allocator, which is SSA-based and used by FreeDreno and the Turnip driver. And I'm Daniel. I probably started all this hype about SSA-based register allocators when implementing it for the Acro compiler used by the Redvi driver. Before we jump into the register allocation stuff, let us quickly recap the SSA form. Whoa. Okay, there we go. SSA stands for single static assignment, and instead of variables, we have the values, which are only defined once. You probably already know all this, but let us go over it anyway. So when a variable is written multiple times, we insert a so-called phi node to produce a new value that is equal to either value, depending on which path the control takes. So the phi node isn't a real instruction, as most computers don't have phi instructions, but it's very useful for all kinds of optimizations. And for that reason, the SSA form is used throughout the middle end by most modern compilers. Also note that here in this example, or also in general, each source of a phi node is associated with a predecessor block. And each source is considered to be read at the end of the corresponding predecessor. So in this example, V10 is read at the end of the then branch, and V11 is read at the end of the else branch. Before a program can run on any hardware, the phi nodes have to be removed again. As I stated, they cannot be executed on the hardware. So the SSA deconstruction has to be performed, or also known as the SSA elimination, and is traditionally performed before register allocation by inserting copies on the control flow edges. So in these copies, which are then inserted, can sometimes be removed by the so-called coalescing pass. Then register allocation is the process of replacing these variables with physical registers. As there can be an unbounded number of variables in a program, but only a limited number of physical registers, there usually must be multiple variables mapped to the same physical register. But the assignments cannot conflict. So, for example, here we see that V1 and V2 cannot be assigned to the same physical register because the load to V2 would override the value of V1. And to be more precisely, we say that V1 is live during the definition of V2, meaning that it will be used later, here in this example, by the add instruction below. If the register allocator cannot find a suitable allocation, then it might have to move some variables to memory and add load store instructions. And this process is called spilling. We will get back to that later, but as you can already see here in this short example, it is possible to assign the variables in different ways, and not all ways are equally good. So this brings up the question, what is actually a good register allocation? Optimality in terms of register allocation is not only a question of feasibility, meaning that do we find allocation? But it's also a question of the quality of the generated code. And this question is highly hardware dependent. For example, are move instruction or copy instruction, are they cheap or expensive? Are spills to memory cheap or expensive, as there's definitely a trade-off between having more copy instructions or more spill instructions, that is memory loads and stores. Or do we gain anything from using less registers, or can we just as well use the whole register file without any drawbacks? And finally, there's also the question of do we have to take care of read after write stores? Yeah, this will not be part of our talk today. Let's have a look at traditional register location. Register location can be seen, or has, like, for a long time been seen as a graph coloring problem, where variables correspond to the nodes in the so-called interference graph, and the physical registers are the colors. So two nodes in this graph share an edge if they cannot share a register. That is, if they are live at the same time. And this approach shares the same problems with general graph coloring. It is NP complete. Even building the interference graph is comparably expensive. And for that reason, basically as another heuristic, the so-called linear scan was invented. We will cover the linear scan algorithm in more detail later, but the general idea is that in a single pass over the program, the registers are just assigned on the go. As I mentioned before already, coalescing is the process of removing copy instructions which have been inserted by the SSA deconstruction pass. So the traditional register allocator does not insert any new copies in the program, and this means that copies which are removed before the register allocator won't appear in the final program, and we say that coalescing and register allocation are decoupled or can be decoupled. But the process of removing copies makes it harder to estimate the number of registers which are needed for the program to execute, up to the point that the register allocator must be able to insert spill code to proceed, or is otherwise cannot otherwise find a free register. If we look at SSA-based register allocation, the algorithm is, for example, described in the paper Optimal Register Allocation for SSA form programs in Polynomial Time by Sebastian Hack and Gerhard Goos. And one thing to note directly is that the optimal in this paper refers to the minimum number of registers used. And this also requires some assumptions, to which we will get back later. But it is not optimal in the sense that we discussed earlier. Just to keep that in mind. Also, we know that register allocation is NP hard, so in general, you won't find an optimal solution in polynomial time unless you solve P equals NP. The algorithm in this paper is an extension of the graph coloring algorithm. So what we will do in this talk is slightly different, and it's called the tree scan algorithm, but the principle and ideas are the same. The idea of SSA-based register allocation is pretty simple. We just assign registers to the phi nodes and deconstruct the SSA afterwards. So, but what are the implications of this idea? First of all, coalescing is implicit. We may need to insert copies when deconstructing the SSA, after register allocation, or we may not. And this entirely depends on how we assign registers to the fee nodes. The second implication is that on SSA, we can precisely calculate the number of registers we will need in the final program. And for that reason, we can handle spilling independently and before the register allocation. Already know that in order to be able to do that, even more copies might be necessary. Yeah, in addition to the ones from coalescing or from the fee nodes. So what about GPUs? Now that we know a bit about the advantages and disadvantages of SSA-based register allocation, is it a good fit for GPUs? Let's have a look. GPUs rely on having many waves. These are, from hardware perspective, these are threads sharing the same memory and LU resources, so that the latency of waiting on memory can be hidden by switching between the waves. And many GPUs partition the register file dynamically between waves. And this means that the more registers a program uses, the fewer waves can be active at once, also called the occupancy, and creates a complex trade-off between the ability to hide latency in a single wave or to hide latency by switching between waves. And traditionally, the scheduler, which is running before the register allocator, has to make this trade-off, but has no way of knowing how many registers the register allocator will eventually need. So with SSA-based register allocation, we can know exactly how many registers a given program will need. And this allows the scheduler to make better decisions. To sum it up, we can conclude that on some GPU architectures, it is beneficial to use less registers. And also on GPUs, memory bandwidth is typically much lower than the register file bandwidth. Also, the memory latency is much higher than of registers. And that means that any spilling can quickly kill the performance. On the other hand, register-to-register copies are relatively cheap. And with traditional allocators, there's no guarantee it succeeds without inserting spill code, even if there are, in theory, enough registers available. So with SSA-based register allocation, we can do spilling upfront and avoid, or even avoid it unless it's absolutely necessary. And for these reasons, we decided to use SSA-based register allocation for our backends. And Connor will now explain to us the actual algorithm in all its beauty.
Okay, so now you've heard from Daniel about all the benefits of SSA-based register allocation, but now let's dive in and see how it actually works. All right, so to explain it, let's start with a very simple architecture, and later we're going to extend it to support branching and other more realistic things, but the core ideas that we're going to see will remain the same. Okay, so in the simple architecture, liveness is very straightforward. The value is just live whenever there's a use later in the program. However, since our algorithm is going to work top-down for reasons that will be clear later when we go over the tree scan, we're going to need to know when a given use is the last use of a value. We say that this use kills the value because afterwards it's no longer live. So we have these kill flags, as you can see here. And another note, we have to be careful here when there are multiple uses of the same value. Real implementations like Echo and IR3 keep track of the first kill of each value for each instruction to simplify the core algorithm, but we're going to gloss over that here. All right. So for the actual allocator, we need to keep track of which physical registers are available and which are currently in use by a value. Uses happen before definition. So first we mark killed uses as making their register available. And then for each definition, we pick an available register and mark it as in use. And then we just do this over each instruction, going one instruction at a time. This algorithm is optimal in the sense that if there is a valid assignment, it will find one. Specifically, it'll never fail as long as there are most n values live at the same time, where n, again, is the size of the register file. This is called the register pressure, and in Echo, the maximum register pressure is called the demand of the program. It's important to note that this algorithm is actually a restatement of the linear scan allocator that Daniel mentioned earlier. In the usual linear scan algorithm, we use a different data structure called the live range instead of the kill flags, and we iterate over live ranges instead of instructions, but this formulation is going to be better suited for being extended to the tree scan algorithm. We'll see in a second. Okay, so now that we've got our basic register allocator, we're going to extend it to handle control flow, which is the first major extension that we're going to talk about. So first off, for liveness, we're going to use the classic data flow algorithm to find liveness. It's described all over the internet, so I'm not going to talk about it here. But the result of the algorithm is a bunch of live in and live out sets for each block, saying which values are live before the beginning and after the end of the block. And we're going to assume that we still have kill flags as before, in addition to the live in and the live out sets. So before we get to the actual algorithm, we're going to need to go over a bit of theory to understand why it still works, even when there's branching and multiple basic blocks. So in particular, we're going to have to go over the notion of dominance. In SSA, we typically require that each definition dominates its use, which allows that the value is always defined whenever the use of the value is reached. And when converting to SSA, we insert a special fake instruction called undef, and extra fee nodes when a register is only partially defined to keep that property. So we're going to assume throughout this that that's been the case. Okay, so an important fact about the dominance relation that I just showed you is that it forms a tree. That is, given a program organized into basic blocks, the blocks can be put into a tree where A dominates B only if A is B's ancestor in the tree. So here we have a simple program and an example of its corresponding dominance tree on the right-hand side. The key theorem which makes SSA-based register allocation possible is that the live range of an SSA value, that is the places where it is live, forms the subtree of this tree, which is rooted at the definition. So for example, here we have the live range of V1, and you can see that it is a subtree of the entire dominance tree on the right-hand side. Okay, so now that we've gone over this theory, we can get back to our allocator. We're going to extend the previous algorithm by just visiting each block and running the previous algorithm inside the block. But we have to visit these blocks in the so-called dominance order, meaning that we have to visit each block before we visit the blocks it dominates. Most common block orders, such as the source code order in NIR with structured control flow, already satisfy this. So it's not going to be that hard to do this. If we follow dominance order, then we're going to be guaranteed that each live in value will be assigned to a register by the time we visit the block, because its definition has to dominate the block due to the whole tree property. And furthermore, for any two live in values, then one must dominate the other, which means that the first one must have been live during the definition of the second one that it dominates. So they must have been assigned separate registers. This means that each live in value has a unique register, and that we have a valid assignment of values to registers at the start of each block. So all we then have to do is set up the available set rather than just assuming that everything is available at the beginning like we did before, and we can reuse the core of the previous algorithm. Okay, so this allocator works, and it's still optimal in the sense that it uses the minimum number of registers possible, but we still have to deal with fee nodes. One key thing that you have to understand about phi nodes is that they happen in parallel. That because the source of each phi node is read at the end of the predecessor block and then copied to the destinations in parallel at the start of the successor basic block. This means that sometimes we have to swap two registers to resolve a phi node, as we'll see later. So let's look at an example to see what this means in practice. So here we have an example program that I pulled from one of the SSA papers. And the result after SSA construction and very simple copy propagation. Because D is only used in the if, and we only have 3 values in the first place, because D is only used in the if, it doesn't conflict with E. Because we only have 3 values in the first place, the register pressure is never more than 2. So let's assume that our processor has only 2 registers, that is, we'll set n equals 2 for simplicity. If we run our algorithm on this, then what do we get? So this is one possible register assignment for the previous program. Along the if branch, R0 is copied to R0, and R1 is copied to R1. So we don't have to do anything. We don't have to insert any code. However, along the else branch, R1 is copied to R0, and R0 is copied to R1 at the same time, because the phi nodes, again, have to happen in parallel. This means that we have to swap R0 and R1 when coming from the else block. Since we don't have any extra registers available, we have to do the swap. In fact, it's impossible to find an allocation for this program that doesn't involve swapping the 2 registers in place. So this shows that in general, it's impossible to avoid this sort of swapping if we want to use the minimum number of registers possible and know ahead of time how many registers we need. So how do we handle these swaps? Sometimes the hardware has a swap instruction that's already available and just does exactly what we want, or we can use some sort of trick to construct it. But on targets that aren't so fortunate, we need to find an available spare register. For example, by running liveness analysis on the already register allocated program again, and fall back to something like this XOR trick when we run out of registers. Again, I'm not going to describe how this works. You can easily find a lot of explanations on the internet about this XOR trick. But it's good to know that we have it in the back of our pocket in case the hardware doesn't help us. Okay, so now that we've worked through that one small example, let's talk about how it works in general. First off, it's important to note that when inserting code to resolve a phi node, we have to be mindful of the fact that phi nodes are supposed to happen along the control flow edge. If the predecessor block of the phi node that we're interested in only has 1 successor, then it's not a problem because code inserted along the edge for this phi node can be moved up to the predecessor without changing anything. However, if the predecessor has other successors than the one containing the phi node, any code inserted at the end will also happen along those other edges, and it might break things. So if there is a so-called critical edge like this, then the usual solution is to just insert an empty block that can contain our fix-up code. All right. So in order to handle more complicated cases than just a single swap, we need to create this so-called transfer graph. The nodes of the graph are the physical registers, and the edges are the copies. We then resolve the graph piece by piece, inserting copies until there are only cycles left, and then inserting swaps to resolve the cycles. The overall algorithm is pretty similar to the algorithm in this paper for resolving parallel copies when doing SSA deconstruction before register allocation. So I'm not going to describe it too much further. Now, while we can't avoid inserting these copies and swaps, we would like to avoid inserting them whenever possible. To do this, we have to add affinities to phi nodes, meaning that we try to assign the same register for their arguments and destination. Then the pick_physreg function in our pseudocode has to consider these affinities to avoid creating too many instructions when resolving phi nodes. Can't always find the optimal allocation, of course, because as Daniel mentioned, it's NP hard. But we can do much better than a naive pick_physreg implementation. All right. So to recap, we've talked about how SSA-based register allocation works on an architecture with a perfectly registered register file where each value can be assigned to any physical registers, no physical registers overlap, and everything is unicorns and rainbows. This is more or less what was in the original SSA-based register allocation paper. But in the real world, things are never so simple, unfortunately. And also, there's no one-size-fits-all solution to getting SSA-based register allocation to work on an arbitrarily complex register file. However, using what's called live-range splitting, we can extend it to handle most features of different targets. We're going to focus on one feature, relatively common to GPU architectures, but most of the ideas and the basic framework here can be reused for other features. All right. So the feature I'm going to talk about here is vector registers. Most GPUs have some instructions which operate on sequences of registers rather than a single one. Usually these are load and store instructions. We're going to assume that these instructions can take any register as a base and load and store the series of registers after that. But we're not going to allow wraparound because most architectures don't allow that. So we can't load from the last register in the first one, something like that. And so we're going to extend our toy architecture to add vector load and store instructions, and then I'm going to explain how to extend SSA-based register allocation to handle that. Okay, so the first question is, how do we model these vector registers in SSA? I'm going to add two pseudo instructions similar to fnodes called split and collect, or in Echo they're called split vector and create vector. Split vector and create vector, yeah. Collect takes n scalar registers and produces an n-sized vector register. Split does the exact opposite. It takes an n-sized vector register and splits it into n scalar registers. Both of these instructions are essentially equivalent to a series of parallel copies, so we can handle them just like any other instruction, and then after register allocation, we can lower them to copies and swaps using the same transfer graph technique as we saw for fnodes. Again, similar to fnodes, we're going to add affinities for these instructions to try to avoid inserting copies for them whenever possible. Okay, so how many registers? Here's the problem though. How many registers will we need when allocating this program? It should be clear that first off, we need to update our definition of register pressure, since values can now take up more than one register. Instead of the number of live values, the register pressure is now the total number of live vector components. And with that updated definition, we can see that this program has a maximum register pressure of 3 at the beginning with the load and the split there. So what happens when we try to allocate this program using only 3 registers? Okay, so this is the result of that. So we can successfully allocate the first 4 instructions, but then when allocating V4, we run into a problem. At this point of the program, there are 2 spaces available in the register file, but they aren't contiguous, so we don't have enough space to allocate V4. What can we do about this? Okay, cool. One back. So the solution is insert a copy before the instruction to shuffle the registers to make space for V4. There are 2 possible ways to do this. If we want to preserve the SSA form after register allocation, then we can create a new SSA value and rewrite the uses of V4 after the load instruction to refer to this new value. If not, then we can insert a non-SSA copy like we see here with the R2 equals R1 and have any uses of V4 contain a different register than the definition. ACO uses the first approach and IR3 uses the second approach. So unfortunately, with our architecture where vector registers can start at any base, it can be really difficult to find an optimal shuffle, meaning that one that uses the minimum number of copies. So for example, in this worst case scenario, there's one empty space at the beginning, followed by a bunch of 2 component values, which fill up the entire register file, followed by a single empty space at the end. there isn't a single scalar value that we can move around to make space next to one of the empty values, which means that we have to shuffle around the entire register file. Both ACO and IR3 use heuristics to try to use less copies when possible, but there's no register. If there's no alignment for vector registers, then in the end, you need a fallback that can handle this case. But fortunately, this sort of thing does not come off very often, as one might imagine. Okay, so that's all I'm going to say about live range splitting here. I don't have enough time to describe it more in detail. But how does this interact with control flow? So for example, in here, we have a value v1, which is defined for the if and then used after the if. And let's say that it's split. We split its live range in the then branch. That means that after the then branch and the else branch, it's in two different registers. So we have a problem here. Without live range splitting, each definition gets exactly one register. But as soon as we introduce live range splits, this assumption doesn't hold anymore. So if when the control flow merges, those two register allocations have to be merged again by inserting new phi nodes. And those phi nodes can either be actual SSA, similar to the parallel copy instructions. Those can be actual SSA values, or they can contain just physical registers. Okay. I'll go back to Daniel for the conclusion.
Yeah, as you could see, although the idea of the SSA-based register allocation is quite simple, the actual implementation has a few more things to take care of. So yeah, then it in the end becomes rather complex. And we can also already note that on SSA-based register allocation, the quality of the code only depends on the ability to avoid these live range splits, and also to assign the same register to phi definitions and the phi sources. So it's only a question about how many copies do I need for the allocation. Yeah, I know this talk was now pretty fast and dense. So for those who are interested in more details about it and how to actually do in detail single steps of this algorithm, and if you have more ideas to try and stuff like that, then we would like to invite you tomorrow to the workshop at 16:35. And yeah, that was it so far from our side. But yeah, now we have a couple of minutes for questions. Thank you so much. Thank you so far.
Thank you very much for your question, for your talk. And now it's time for some questions from IRC. Although the talk was very intensive, so it might be that some people need a bit more time to process all of that. Okay, let's wait for a few more seconds for any questions coming in. Okay, Eric Nunes asks, if this is implemented in Mesa, is it done in a way that can be easily reused by other Mesa drivers?
That's a good question and a tough one. And I did touch on that a bit when I said that there's no one-size-fits-all solution for handling different register files. There might be something to be shared with the whole liveness, but in order to do that, you have to more tightly couple because this algorithm is way more tightly coupled to the IR than, for example, graph-based register coloring that you can build this graph data structure and then just sort of hand it off to another algorithm. So we don't have any easier answers for that, and that's part of the reason why IR3 register allocation is like a completely separate thing.
Fire asks, how hard is it to add optimal spilling to this approach?
I think optimal spilling by itself is another NP hard problem, but
I think when there's no control flow, you can do the optimal thing.
okay.
But because you can use that least recently used.
Yeah, so the point is, by separating spilling and register allocation, it is possible to use way better heuristics than just like in the traditional register allocation, you basically run into, oh, I have no registers anymore. What should I do, or which variables should I spill? While when doing the spilling before register allocation, you basically analyze the program and see which parts need more registers than are available and spill around it. So I think that you can do much better even with kind of simple heuristics than what is done in the traditional register allocation.
Yeah, it's definitely way better. And I think, yeah, people were using that technique even before with like graphical and register allocators, but then you still might need to spill during register allocation. But you can do it kind of perfectly with SSA-based register allocation.
And you can also avoid it in 99% of the cases. Well, then a bit depends on your architecture and how many registers are available and stuff like that, but yeah.
Okay, looks like that was the last question. Thank you very much to Connor Abbott and Daniel Sherman for this talk. And if you're interested in hearing more, there's a workshop tomorrow. Check out the schedule. And well, have a great conference. Thank you very much.
All right,
thank you. Goodbye.
Okay, and I didn't think so. And we are ready to go with the next talk of the day. Christian Weiner is going to present us the status update on Etnaviv display driver for Vivante GPUs. Christian, take it away.
Hi, and welcome to my talk about Etnaviv Status Update 2021 edition. If you don't know this lovely guy in front of you, my name is Gmeiner Christian, and I'm a long-term Etnaviv developer. So, let's get started. I want to start with some personal warning. I'm mostly presenting here my point of view, my thoughts about Etnaviv, how the last year was going, what is coming, and if some company, etc., is working behind closed doors on stuff that I'm not aware of, I'm sadly cannot present it. So let's start with a basic overview for everybody who does not know what Etnaviv is. Etnaviv is an open source graphics driver which supports embedded GPUs from Vivante, and all the work is done through reverse engineering. Etnaviv was upstreamed in Mesa 17.0, and we support, support a wide range of different GPU models. The nice thing about the Vivante GPUs is that it is quite easy to get them working. Mostly all the hard work is done to get the kernel, to get it at the kernel level right, to get your power, clock gating, interrupt stuff working. And the chances are quite high that you get a quite nice out-of-the-box experience with Etnaviv. So let's talk about the current state as of today. Yeah, it's not that easy. We still do not have access to any official documentation about how the GPU is working, about the instruction set architecture. Also, we are not that many developers working on Etnaviv, which is quite sad. And I'm not really sure where the big problems are that other people are joining us. I think it could be the documentation, but yeah. Also, I think thanks to COVID, a lot of companies stopped their efforts in supporting the work we are doing financially. And so I need to say that for me personally, Etnaviv was downgraded to be just another hobby that, needs to split my free time. So it's just a hobby for me. So my involvement got a little bit less during this year. Nevertheless, there was some work done during the last year, and I would like to start on the kernel side. The last, I don't remember, 2 or 3 weeks ago, Lucas Stach from Penguitronics finally was able to fix some really wild MMU issues where depending now where the state of the MMU, the GPU sees and the GPU managers are not the same, and run into a lot of troubles. And I'm really thankful that Lucas did a nice job to fix these issues. Then on the kernel side, there was some new entries to support some variants of the GC7000 models. In the kernel, we have something called like a hardware database, where we can get the details, which features are supported, if we cannot trust the register values returned by the GPU model. And also there was some basic maintenance around the DRAM subsystem. On the Mesa side, there was a little bit more exciting stuff that landed. We were able to add DRAM shim support, which is a really nice thing because it enables you to run the full compiler stack, shader compiler stack on a normal development machine where you don't have a Vivante GPU in it. So this is a very helpful thing if you do, or if you're into compiler development for Etnaviv. Then we were able to land the shader compiler cache to speed up the starting of games, for instance. We were able to add the so-called NTE support. This enables us to expose more fragment and vertex samplers if the GPU supports it. Then there were fixes all over the place. We have fixes for alpha blend, for depth and standstill. There were some locking fixes done by a developer. And also we are doing basic maintenance these days, because NIR and Scallium are quite fast moving targets these days. So yeah, you need to keep up with the speed of development there. And also we had some NIR stuff, but I will talk in more detail a little bit later. So let's start with one very important thing, continuous integration. These days, everybody wants to have some kind of CI integration, as it allows you to have more testing of patches of merge requests in an automatic way. Before you have a CI, you need to do manual testing and check if the behavior is equal on all supported GPU models and you do not introduce any regressions. And for this, I started to look into this topic about a year ago. And I think it's finally time for an Ethernet CI solution that is based on bare metal solution from FreeDesktop. On my side, it's running, the GitLab run is running in an Android installation. I'm using a dedicated setup with a CR2net to have the console logging. I have an Ethernet-based power control. So here we see a picture about a year ago that I showed last XDC. The setup is basically the same. I have more devices to test, and the whole CI farm moved to another room. So what is missing to get live with CI? I'm happy to say, as of yesterday, there are no showstoppers anymore. There is an official merge request to integrate EtherNaviv into Mesa's CI landscape. And I hope to land this merge request in the next few days. So, to the next topic, NIR. Everybody wants a NIR compiler these days, and we have some problems on EtherNaviv side. The biggest problem, the original author of the NIR compiler is not active anymore. And the result is that the maintenance is quite hard, that nobody is really into it to fix problems, to rework the overall architecture of the compiling stack. We are triggering some NIR validation problems because we are doing some funny things with NIR instructions. And as a result of this, there was a start of some cleanup and refactoring work. And you might think that a refactoring process is stupidly simple and everybody can do it, and it does not take that much time. But it is a lot of work to do this refactoring stuff. In the end, it looks like this. You try to run ShaderDB with DRAM shim and capture the generated shader code with some statistics about number of instructions, used uniforms, and stuff like this. Then you try a really simple refactoring step, like taking out, 10 lines and push it into a separate function so that you can easily write unit tests for it. You rerun the ShaderDB stuff and everything falls apart. You now have 10 times of instructions, you use 2 times of uniforms, and now the fun part starts. You need to dig into the NIR optimization passes that are happening. You need to check the ordering of the passes. You need really to understand what's the problem. When you figured out what's wrong and you fix it in your code, it's time, usually for me, to write unit tests to keep it working over time. Because, the refactoring process happens a lot of times. There's a repeating process. When you're happy with your results, the unit tests are passing, usually you need to then run some real world or some conformance tests. Usually I run DPQ and Piglet to be sure that I do not introduce any regressions. And as I told you before, this is a quite time-consuming task to clean up the overall architecture. So this process takes some time. But there are benefits doing this that way. In the meantime, since the last year, we landed a lot of cleanups. There were crash fixes. There were really bad crashes when running Piglet with the near compiler backend. We were able to move the near-based directory texture lowering from EtnaWith out in the state tracker and converted VC4 to UC2. We were able to land some compiler optimizations, and I think it is now really time to make it the default, because I often get asked by other people when I enable near as default compiler backend for EtnaWith, and I think now it's the time. I hope there are not too much regressions out there in the wild, because I cannot test everything, but I think it is really now time. So as I got then a little bit bored with this near stuff, with this refactoring cycle I'm doing, I started to look into another very interesting topic. It's called EtherSpec. It's quite the opposite in the compiler stack. It's the low-end layer, which deals with the instruction set architecture, compilers, assemblers, and stuff like this. And I'm quite sure Freeduino uses this. In the end, it is a way to describe your ether and with XML-based files, and it generates for you a disassembler and assembler, more or less decoding and encoding of the instruction set. So this is really, really helpful, as by now there are some unknown bits in the Vivante EtherSpec. So yeah, there was one little problem. EtherSpec was designed for Freeduino, which has a maximum bit set size of 64 bits. That is not enough for EtnaWith. We need 128 bits for our instruction set. We have also a fixed size instruction set, but the size is much bigger, so we need to fix this. And there is now a merge request to improve EtherSpec in that way that we can reuse EtherSpec for EtnaWith. I hope that this merge request also lands quite soon, and that the EtnaWith specific Ether XML file will follow shortly afterwards. But this merge request is now open for more than some weeks, and I really hope to push this forward by talking publicly about it. So, what might be the future bring for EtnaWith? As I told you, I'm really into now kicking off the DJSI compiler and switching to Near, as it is the only way out of this disaster. I need to maintain at the moment 2 compiler backends, and that's not going to work, especially since EtnaWith is more a hobby now. There's still hope to land or to have anytime soon Class 3 support. But my main focus for the next months is more or less to fix or emulate broken stuff or missing stuff on the current features that we have. I want to have a nice baseline I can build up onto. I'm not interested in throwing in some Class 3 features in a hacky way, because I think that is not going to work in the long run, because I really want to have a nice maintainable driver with a lot of unit testing in it to keep it stable and not regressing that fast. That's more or less it from my side. if you're interested into Edna with development, please join our IRC channel and get involved. We really need more manpower.
All right. Thank you very much for your talk. And now it's time for questions. So we're waiting for a little bit for people to catch up on the talk. And in just a few seconds, we should see some questions, hopefully.
Hopefully.
Okay, it looks like we don't have any questions at the moment, so we will probably move over to the IRC for any future questions should someone be interested further.
Yeah, that's
and
fine.
Until then, thank you very much for your talk and have a great rest of the conference.
Yeah, thanks. Bye.
Thank you. Welcome back. It's time for one more talk for today, and that's Fast Checkpoint Restore for AMD GPUs with Creo. Let me present you the talk by Rajneesh Bhardwaj, Felix Kuling, and David Yat Sin.
Hi, my name is Felix. I'm a technical lead in the Linux kernel mode GPU driver team for computing at Advanced Micro Devices. My collaborators on this project are Rajneesh Bhardwaj and David Yatsin, who are both engineers in my team. And we're going to present the fast checkpoint and restore for AMD GPUs with Creo. So what is Creo? Creo stands for Checkpoint and Restore in User Space. It's an open source project supported by the Linux kernel community that provides functionality to save the complete state of a running process, including its open file descriptors, its memory contents, and so on, in image files on the file system, and then restore those on the same system or on a different system, which is useful for process migration, container migration, forensics, debugging, all sorts of use cases. The problem is that currently Creo does not support checkpointing and restoring processes that use device drivers directly, like user mode device drivers. Basically, any process that opens a device file cannot currently be checkpointed with Creo, because those device files and the device drivers underneath have state that is unknown and invisible to Creo. There is no native support in the Linux kernel to expose that state to user mode to allow it to be checkpointed and later restored. So that includes things like buffer objects in VRAM. It includes GPU virtual address mappings and user mode queues in the case of our compute GPU driver. So fortunately, the Creo project had the foresight to add a plugin mechanism to allow adding support for specific device drivers in the future. This is supported by basically shared objects that are loaded at runtime and that provide certain callbacks that are called from hooks inside the Creo code itself. However, to my knowledge, there don't exist any useful plugins for real-world devices for Creo at this time. We are the first ones who are attempting to implement that, and we actually found that in the process we needed to add a few extra hooks to Creo that didn't exist before, just to be able to do what we need to do. So with that, let's take a look at the high-level architecture of Creo. So Creo saves a hierarchy of processes, or a tree of processes, starting with a parent task, and then including all its child processes and their child processes and so on. On restore, the same processes, the same tree of processes gets restored using the same PIDs, the same permissions, the same open files, memory contents, and so on. So when Creo creates the checkpoint, it uses ptrace to attach to the running processes, and it stops and freezes their execution, similar to what a debugger would do. And then it uses that to inject some parasite code into the process that helps it drain certain resources from that process, things like file descriptors, signals, timers, events, and so on. And it does that through remote procedure call kind of API through the ptrace system call. And one of those RPC functions is a zero copy to save the RAM contents, the memory contents from the child process. This VM splice system call provides a mechanism for mapping pages from the target process into the Creo process and avoids an extra copy in system memory when the system memory contents are saved. Then Creo serializes all that data using Google Protobuf and writes that to disk images. On restore, that's kind of the reverse process. So you start Creo with a certain command line to say, I want to restore this set of images. And so Creo goes and forks all the original process hierarchy and sets up piece of position-independent code inside each of those child processes that is later needed to finalize the restore process. And then each child process, which is basically a clone of Creo, goes and transforms itself into the original process that was previously saved. So each process takes a different set of images and restores itself to the state that was saved earlier in the checkpoint phase. The restoring of those several processes is synchronized through several stages. And one of the last stages, or pretty much the last stage, each of those mostly restored Creo processes jumps to the PIC code. And that PIC code is at a virtual address location where it does not conflict with any of the original virtual address mappings of the checkpointed process, so that that code can restore the original virtual address mappings, basically remap all the VMAs to their original locations without overriding itself. And so then the last thing it does is basically it unmaps itself and returns control back to the restored process through an RT sig return mechanism. So how did we add support for ROCm, basically for GPU accelerated computing to Creo? So there are three pieces to the work that we did here. We made some modifications to Creo itself. That is, we added a couple of plugin hooks for things that were not originally supported by the Creo plugin architecture. We added support for dealing with device file VMAs, so basically VMAs that map pieces of a device file. And those changes are currently under review by the Creo community. There's a link here to a pull request. Then we have our AMD GPU plugin, which will be built as part of Creo, and we're expecting to upstream that to the Creo community. So the current work in progress can be found on GitHub. And the last piece is changes to our KFD kernel mode driver. So we're adding ioctl APIs to support saving and restoring the state of basically the GPU or the GPU buffer objects and user mode queues and so on for Creo. That part is under review on the AMD GFX and DRI devel mailing lists, and the current work in progress is also visible on GitHub. So the plugin that we created supports several device files. So every ROCm process opens /dev/kfd, which is the API that we use for dealing with all the user mode queues and signaling, memory management. And they also open the DRI render nodes. Currently, this is mostly used for CPU mapping of buffer objects. So all of these device files need to be supported by Creo in order to successfully save and restore a ROCm process. And so what the plugin does is when Creo creates a checkpoint, it drains all the GPU state from KFD through new ioctl APIs that we created. It copies all the VRM contents using the SDMA engine, and it supports multiple GPU. It supports ROCm compute applications. It currently does not support applications that use other graphics or compute APIs like Vulkan Compute or OpenGL or Mesa's video decode and encode acceleration. Yeah, and then it saves all the saved state to Google Protobuf images, just like Creo saves all the state that it supports natively. So the plugin provides 5 plugin hooks now. So there were 2 existing hooks, dump ext file and restore ext files, that already existed in Creo for dealing with ext file stands for external file. So these are files that are not natively supported by Creo and can be used for dealing with device files. So the dump ext file saves all the KFD state and all the VRM contents, and the restore ext file takes all that state from the images and sends it back to the KFD kernel mode driver and restores the VRM contents. However, there are a few extra steps needed in addition to that in order to successfully restore a process. So one of the new hooks we added is to update the VMA map. So when we have CPU virtual address mappings of the render nodes for CPU mapping of our VRM buffer object, for example, these mappings associate each buffer object with a specific offset within the device file. And that offset can change when we restore the process with Creo, because basically when Creo restores the process, it creates a new set of buffer objects that kind of mirrors what was saved in the checkpoint phase. But we don't have a good way of recreating those buffer objects with the same offsets. Those offsets are system-wide, basically global. It's a global kind of address space, and so there's no good way to guarantee that we get the same offsets back after restoring. Also, the name of the device file can change. For example, we might choose to restore the process on a different set of GPUs or on an entirely different systems where the naming of the device files is different. So we have to be able to basically restore those VMAs with different device file names and with different offsets. Then we have a new hook for resume devices late. So this is called at the final stage after all the VMAs have been restored to their original virtual address locations. And so we have to wait until this very late stage, which is way after the restore ext file stage, to resume execution of the GPU queues and to restore MMU notifiers that are sensitive to the virtual address mappings and their virtual addresses. And finally, we added a handle device VMA plugin hook. So that basically is a query for Creo to say, I'm seeing a VMA for a device file. Do I have a plugin that supports those VMAs? And so in the case of VMAs for DRA render nodes, our plugin will return, yes, we know how to deal with this. So you can safely save those VMAs. And then we have a number of ioctls in the kernel mode driver to support the checkpoint and restore process with Creo. These APIs are currently under review in the AIM-GFX and DRI devel mailing lists. All of these APIs have some security considerations, and there's a separate slide about those later on. And they're called from different contexts. Some of those APIs are called from a Creo process, a remote Creo process, and they need to access state of a remote target process. And so we depend on ptrace attachment to basically allow access to those processes. Then we have the restore API that runs in the context of the target process itself, that is restoring itself, and the resume API that again runs in a remote process, basically the master Creo restore process, and controls the resuming of execution and all the child processes that have already restored themselves. So the first three ioctls, pause, process info, and dumper, are all used during the checkpoint stage. So the pause ioctl makes sure that the execution of the user mode queues is stopped, or as we call it, the queues are evicted. So this makes sure that the snapshot that we create after that is consistent and static, and so we're not trying to save something that's still changing as the GPU is executing. This pause ioctl supports both stopping the execution and also resuming the execution. Basically, once we're done creating the snapshot, we can resume the execution of the user mode queues because Creo can optionally let the application continue running after it's taken the snapshot. Process info returns all sorts of information to user mode about what type of objects and how many of them and what memory size we need to save all the state. So it tells us how many buffer objects there are, how big they are, how many queues there are, how many SVM virtual address ranges, and so on. And then the dumper ioctl does the actual saving of state. So basically, at least one ioctl call for each type of object that we support, like a buffer object or like buffer objects or user mode queues. But we can also break that into multiple calls to avoid running into file descriptor limitations, because each of the buffer objects that we're saving comes with a DMA buff file descriptor for saving the memory contents. The restorer ioctl is the reverse of the dumper ioctl, except it runs in a different context. But otherwise, it takes the same type of information as the restorer ioctl. Just instead of saving the information to user mode, it copies the information back from user mode to kernel mode. And finally, the resume ioctl is the one that finalizes the restoring of MMU notifiers and SVM virtual address ranges, and finally resumes the execution of the GPU queues. So here we have a short animation that kind of visualizes what this process of checkpointing looks like. So here we have a set of several processes, and so we're showing here how process 1 will get saved by Creo. So the process is some ROCm application, so it could be an HPC application or a machine learning workload. That includes the application code, all the libraries and frameworks it's using, the language runtime APIs, and the ROCR runtime. And then in kernel space, we have the AMD GPU driver with a KFD portion that provides the KFD ioctl API. And we have Creo with our AMD GPU plugin that basically coordinates all that checkpointing process. And on the hardware side, we have a system with one or more GPUs and a mass storage device for saving the images. So the first thing that Creo does is it attaches to the target process using ptrace. And so it injects the parasite code into the target process and then uses that to drain all the information from the target process, like the file descriptors and memory contents and so on. Then it calls the AMD GPU plugin as it goes through the list of open file descriptors and finds our KFD and render node device files and makes those plugin callbacks that initiate the checkpointing of the GPU state. So the plugin calls into the kernel mode driver through the KFD ioctl APIs that we added, and then drains all the state from the kernel mode driver, which includes the device topology, the memory allocations, the virtual address mappings, user mode queues, and so on. And finally, when that's all done, the process gets terminated by Creo, and the images are saved to disk, and then they are ready for migration to another system or for restoring on the same system or for forensic analysis of what was going on while the process was running. So there are some security considerations with what Creo does. So there are a couple of potential threats that we need to keep in mind. So when Creo accesses the target process, it has full read access to the entire state of the process, and that's by design. But we have to make sure that we're not giving Creo access to processes that it's not supposed to access. Then we have control of the remote process execution. So for example, when we're taking the snapshot, we have the pause ioctl that stops the execution of the user mode queues and then resumes them later. And when we are done restoring the process, we have the resume ioctl that basically starts execution of the user mode queues at the end of the restore process. And also during a restore, we have write access to some privileged hardware state that was saved by Creo. And so we have to be careful that we trust that privileged hardware state, or if we cannot trust it, that we sanitize it. So for read access, during the checkpoint process, we rely on ptrace. So the ptrace system call already has some security checks based on kernel security attributes, whether a process is allowed to access a remote process through ptrace. And so if ptrace has given access to a remote process for Creo, then we can use that to also grant access to all the GPU state of that process. And so we're basically just piggybacking on the security checks that ptrace already does, and we don't have to reinvent our own security policy here. For remote process execution, in the checkpoint stage, we're using ptrace again. So if ptrace is attached to the target process, then we can also allow execution of the control of the execution of the process. And during the restore, we currently require cap sysadmin. So it basically means the restore process needs to run as root, which is currently a requirement for Creo anyway. And so only root is able to resume execution of the restored process at the end of the restore process. And finally, for write access to the privileged hardware state, that's part of the restore process. Again, cap sysadmin comes in handy, so we require that Creo is a root. Yeah, just the consideration here is that Creo runs as root, and Creo needs to trust the images that were saved earlier and make sure that they are trusted before calling those octals. We are going to discuss that with the Creo community as well. So if it turns out that those images are not trusted and we have to potentially sanitize the state, the privileged hardware state, so we have to go through anything that looks like hardware state and make sure that there's nothing in there that could potentially damage or compromise the system. So now Rajneesh is going to walk us through a short demo of how the checkpoint and restore works with Creo.
Hi everyone, my name is Rajneesh and I work for AMD as a Linux kernel engineer. Today I'm going to show you a demo in which I am going to checkpoint and restore a ROCm application running inside a Docker container. So my hardware is a Ryzen 7 based machine with a Vega 10 Graphics 9 series GPU installed on it. So I'm using a single GPU system for this demo, and my kernel configuration is this 511, which is basically a modified AMD GPU driver. And all the patches that we have used to modify this driver are available on our GitHub page for ROC kernel driver under Creo work in progress branch. We are currently making some design changes to the APIs, and once that is finalized, they will also be updated here. So this is where the kernel changes are present on our GitHub page, and on the same Radeon Open Compute GitHub page, we also have our forked Creo repository that contains all of plugin work that we are doing to make it work. This is basically the user space component, and this is the kernel side work. So now let's get back to the demo. So let me first start the transformers application. So while it initializes, I'm going to switch to another shell and see the current GPU usage using ROCm tool. So you can see the application is still initializing. And it's going to take a few seconds to fully initialize the PyTorch application here. So now you can see that the workload is now running here, and the current GPU utilization is about full, and approximately 70% VRAM is occupied. A few more things. Let's first check whether Creo is installed here. So Creo is installed, and let's check whether all the dependencies are met for Creo. So Creo looks good on this machine. And this is where our AMD GPU plugin should be installed inside var lib Creo. With that, let's now notice the process ID of this workload, which is 11967. So now let's use Creo to checkpoint this. So the command line I'm going to use will have some extra command line options like link remap, TCP established, and file logs for this type of workload. So once I press enter, you will notice that the workload that is running will be paused for a few seconds, and then it will be killed once the checkpointing operation is done. So now the workload is paused, and the Creo is draining the VRAM content and the GPU state using this plugin. And in about 8 seconds, you can see that the application is killed, and the state of the GPU, the VRAM, and everything else that was associated with that process is now saved to disk among these many files. So all these files are generated by Creo with a couple of extra files that we generate as part of our plugin. And the files that are of interest here are KFD image file, which is about 5.4 gigabyte in size. My GPU VRAM is about 8 gigabyte. So around 5.4 gigabyte was in use when this work was going on, workload was running. And the other one is rendered image file. So this doesn't contain much, but just some metadata that we use to checkpoint and restore. But this could be used in future to export more graphics related state here. So now let's try to restore this application using Creo restore command. Let's see if it restores successfully. And you see, in about 5 to 6 seconds, the application is back to its execution state again. And we can go back to the other terminal and check the same statistics about the GPU usage. So you can see approximately same 69% VRAM is used, and GPU is about fully utilized here. So with this, I conclude the demo. Thank you for watching.
Thank you, Rajneesh. And that brings us nearly to the end of this presentation. So just a quick status update of where we are right now. So as we have both said, we have every intention to fully upstream all this code. Everything is already available on GitHub. So our current work in progress is on GitHub, and we have already started initiating pull requests to the Creo community for some of our work in Creo itself. Also some earlier versions of the plugin code. And also we've sent code reviews of the KFD octal APIs to the AMD GFX and DRI devel mailing lists. So we're currently working on finalizing some of our APIs. They are going right now through a major redesign to make them future-proof and maintainable. And we're finalizing HMM support. So with HMM, we have this new shared virtual memory API in KFD, and so we're supporting that with Creo as well. So the next steps for us are finishing that work that I just mentioned and going with the respective communities through the code review and acceptance process for upstreaming. and eventually get the Creo pull request merged in Creo as well. And then we have some more plans for improving the image size and for speeding up the checkpointing and restoring further. That's it from me. Thank you very much for your attention, and let's get to questions and answers.
All right, that was fast checkpoint restore with AMD GPUs with Cryo, and now we have time for some Q&A. Vinimo asks, how much is missing from making Creo work with graphics? Could this be used in the future to restore the VRAM contents after a GPU hang?
Yeah, so let me take that. There are a few aspects here. One of them is supporting the graphics APIs. That would require some additions to the DRM APIs on the render nodes. Currently, we only support the compute-specific state, not the graphics state. But that's something that we're thinking about anyway, because we need it for supporting our video decode and encode acceleration. The other thing is when you have a graphics application, then you also have additional state that you need to consider. You have connection to an X server, you have server-side state that needs to be handled. And so right now, I don't think that's that would be easy to handle, or I would know how to handle that. And lastly, if you want to protect state across a GPU reset, well, your GPU needs to be in a good state when you're taking the snapshot. So you would have to take that snapshot before the GPU hangs. So if you have some kind of scheme where you're taking periodic snapshots, then you can restore the last good snapshot after you've reset your GPU. So maybe that's a useful scenario. But I don't think it would work to kind of take a snapshot after you've detected some GPU hang.
Okay, one more question from Vinimo. What is the currently intended use case? I'm afraid I didn't quite get that.
Yeah, so there are probably a bunch of use cases. The Creo website lists many use cases. The one we're focusing on right now is for migration of compute applications and data centers.
All right, and one more from Bas Nieuwenhuizen. Are there any ideas on whether this could be made to work to restore on slightly different GPUs, say an APU versus a full-fat Vega or so?
Yeah, so we're not planning to do that. Right now, we have pretty strict checks to make sure that the GPUs that we're saving and restoring on are compatible, which includes things like memory size, number of compute units, instruction set architecture, and so on. So Vega, like a full-blown discrete GPU Vega and an APU, they would not be compatible in that way.
Okay, looks like that's it for questions for now. I'll invite you back to IRC for any further audience questions should they come. And then thank you for the talk and have a great rest of the conference.
Thank you.
Thank you.
Thank you.
Okay, looks like we're ready to go with the next talk of the day, and that's going to be Sumera Priyadarshini with emulating virtual hardware in VKMS.
Hi everyone, I'm Sumera Priyadarshini, a software engineer from India. I'm currently working as a junior software engineer at Polar Signals. I am also a kernel contributor and worked as the Linux kernel outreach intern for the December 2020 cohort, along with mentors Daniel Vetter and Melissa Wen. As part of my outreach project, I worked on the VKMS driver, which is the virtual kernel mode setting driver. That's a software-only model of the KMS driver. The basic idea behind this driver was to be able to test and validate code for virtual displays without necessarily requiring hardware support, which would be very useful in a headless machine like CI. My project mainly involved working on two parts of code. One of them was the VKMS driver, which is part of the GPU subsystem. The other was the test suite for graphics driver, that is the Intel GPU tools suite. Add two features to my, as part of my internship, I decided to add two features to the VKMS driver. One of them was to expose the VKMS driver through the config.fs file system. This would allow us to test multiple instances of VKMS at the same time. The other part that I wanted to add was to implement a virtual hardware or a vblankless mode. Currently, VKMS mimics actual hardware using vertical blanking interrupts, but we wanted to introduce a mode where it can also emulate virtual hardware, that is hardware used in virtual machines like QEMU or KVM. So we essentially wanted a mode without vertical blanking interrupts, that is a vblankless mode. However, a month into the internship, after we had done some prep work for the config.fs file system and I had explored the subsystem a bit more, I realized that it's probably not a feasible goal to do both parts given my internship timeline. So I decided to change my expectations a bit and readjust goals to something more reasonable and to just stick to emulating virtual hardware mode for now. The goal was to have the test results preserved at the end of this patch, except the subtests which depend directly on vertical blanking interrupts. Now for the implementation. As prep work for adding virtual hardware mode, we first needed to change the VKMS composer functions a bit. Now, we wanted to have a separate composer function, which would be called in the vblankless mode. So we wrote a common VKMS composer function. This function would be called by both the virtual hardware mode and the normal mode as well. Then what we did was we added the atomic helpers for the virtual hardware mode, and yeah, that was it. So to come to this point, it took me a fair amount of time because first I had to understand the atomic interface, which was very new to me. I also had to use ftrace to understand the flow of things and what exactly interrupts are and how they affect the rest of the code, and what is the sequence of functions and what parts do we need to check out for errors and all. But once this was done and we introduced that atomic helpers and refactored the composer, I thought my work was done. The tests also passed, which was good. Since the tests passed, I sent in the patch. But, yeah, there's always a but. And turns out I had not felt the need to check the dmessage logs for the tests that had passed. I had only looked at the logs for the tests that had failed. When my mentor pointed this out to me, I looked at the logs and they were full of memory allocation errors in the KMS flip tests. Further, all subtests with interrupts were causing a kernel panic. So the next step was obviously to figure out how to fix these tests. Right, so turns out there were two errors. One of them was being caused by the composer using ksalloc to allocate frames and was easily solved using kvmalloc instead, because kvmalloc does not need to allocate physically contiguous memory locations. And since the kernel page size is only like 4 KBs for my machine, hence ksalloc was not really able to allocate size, the requested size here. The other error was a flaky vmap allocation error, which though was already present in the subsystem, but it was sort of interacting with my patch to give a kernel panic. Thankfully, this error was solved by Thomas Zimmerman, who fixed it in his patch for using shadow buffers in VKMS. And suddenly the error disappeared after a rebase. So I thought we were good to go. And but no, the CRC tests still failed. Since CRC is calculated around vertical blanking interrupts, and we disable the vertical blanking interrupts, so all the CRC tests are failing. Now we need to implement CRC as a one-shot operation. However, that would take a lot of testing and also a lot of refactoring, which maybe is best left for another patch. So for now, we are just modifying the atomic helpers to skip all the CRC tests. Once we did this, right now all the tests either skip or pass, and the results are mostly preserved. So yeah, I've sent in that patch, and let's see. I'd like to talk a bit about what I learned during this internship. One of them definitely was writing idiomatic C, being familiar with tools like ftris, Chemu, and getting comfortable with Git. Another one was how to not get tests to pass and to understand trade-offs around locks and interrupts. I also learned about the atomic interface, which is used so extensively in the graphics subsystem. Something else that this internship really helped me with is to be able to ask for help every time I was stuck. I used to be very scared to do this earlier, and but I'm more or less comfortable asking questions publicly now. Also, something else I really learned is that planning ahead, researching potential roadblocks, and having grace time to be able to catch up is also very important. And there were some side quests, like some other work that I ended up doing during the internship as initial tasks. I think they're minor fixes, but they really helped me get familiar with the VKMS driver. And as for future work, I want to continue to contribute to the VKMS driver. And I would like to continue with the configFS work, and also come up with a way to implement CRC for virtual hardware in vblankless mode. I would like to take this time to thank my mentors, Daniel Vetter and Melissa Wen, for being so patient and nice while teaching me so much and not giving up on me. I also want to thank Sage and Vaishali and Helen and all my other fellow outreach interns who've made this such a great experience. I think my biggest takeaway from this internship was that software is just not about pushing code, but also about building communities that are inclusive and diverse, and therefore more productive. I want to thank everyone in this community for making it such a safe and inclusive space. If you'd like to reach me, here are the ways, and please let me know any questions you have. Thank you for listening to me.
Okay, this was Smara Priyadarshini with emulating virtual hardware in VKMS. So right off the bat, you have salutations from Daniel Stone that it's awesome work. Great, congratulations. And now we have some time for questions. Now let's give people a few seconds to catch up on the talk. It's probably a little bit behind on the stream. Okay, looks like we don't have any questions right away, so please do give a shout out to IRC in case. Oh, no, we have one question here. Are there projects actively using VKMS already?
Hi. To my knowledge, as far as I know, not right now. We're still figuring out a way to use it within CI.
Okay, and it looks like this is it for question. Oh no, Daniel Stone is trying to explain in IRC that there is one use case that they are using it for CI in Weston. Okay, and now Daniel Vetter asks, what's the biggest hurdle that should be fixed for people ramping up on DRM drivers?
I'm sorry, I don't really understand ramping up as in.
Okay, what's the biggest issue that should be fixed for people trying to learn how to work with DRM drivers?
I think slightly maybe better documentation. As a beginner, it took a while for me to understand the terminology and all. So it's something that I would like to contribute and help improve. But yeah, I think otherwise it's a great community to be part of it.
Okay, looks like that's it for the questions for now. Thank you very much for your great talk, Samara, and well, welcome to the community. Thank you,
Thank you
and
so much.
have a great rest of the conference.
You too. Thank you. Bye.
Bye-bye. Good day and welcome to this conference's first lightning talk block. This is the last block of the day, and things get a little bit turned around because we just get some confusion on the organizer's side. But we're now ready to go with the first block in the lightning talks. So first up is Arthur Rasmussen presenting libvfio and Hyperborea. And now, Arthur, the stage is yours.
Thank you so much. So yeah, this is Michael. He's my co-founder, or not my co-founder, he's my co-author of libvfio. Yeah, so we're going to present just a couple little slides for an intro, and then we're going to get going with our demo. So I'll share the screen. So let's see if we can do that. Okay, so if you can see my screen now, I'll just pull this up. Yeah, so we're from a company called, you're probably seeing the second slide page, that's fine. We're from a company called Arc Compute. We work here in Toronto on open mediated device drivers, among other things. So this is kind of our mission statement. This is sort of stuff we're working on. So virtualization today in GPUs. GPU multiplexing is either locked to big companies with expensive hardware, so stuff like NVIDIA Grid, or it sucks. So AMD's GPU IoT module kit, which is fortunate. And the other thing that we see as a problem is modern GPU scheduling and load balancing features are missing from consumer operating systems. So these are our solutions, which we're making open source today. It's so libvfio is the library that powers a lot of our stuff. Hyperborea is our hypervisor tools. Those things start to plug. They plug into things like NVMM in NetBSD and also into KVM in Linux. So we think we have some of the ability or some of the tools that we have to drive things that are a little bit faster, better than some of these other things. Some of the features that we're enabling on this, we're allowing it to work on consumer cards for both, NVIDIA and AMD, but we're also targeting Intel's DG series graphics cards that are sort of on the horizon. And just before I start, a typo on this, but I did want to make clear I'm standing on the shoulders of giants when I'm doing all this work. So Wendell Wilson was one of the guys who helped me really early on with some of this work. Jeffrey McCrae-Gniff, I read his blog posts all the way through writing the stuff. He's been instrumental, I think, in a lot of these things. Michael, who fixes my code, which is frequently broken. James, who is somebody who's helped us a lot with our company, and Shervin and Sander, who are both software developers with us. So very helpful. So with that, I will pop over to just do the demo now. So I'll go back to screen share here. Second, if I can do that. Yeah, so here is a host system running Hyperborea and libvfio. What we've got here is obviously some programs that are running in Linux. We have, you can see here, this is Felix Gears, which is running. And we also have Tux Racer over here that's running. But what I'm going to now do is I'm actually going to, using one graphics card, I'm going to start a virtual machine. You can kind of see what's going on with the text. Probably can't see it with great clarity because it's a monitor behind me. But what we're doing is we're parsing IO MMU groups, which are exposed by the MMU controller in the sys directory. We're looking through all of that. We're finding appropriate devices like NVIDIA cards. We're creating a mediated device, so a device driver which is passed via VFIO into a guest. And we're doing that while actually sharing the graphics resources for the host system. So if I really quickly show this. So you can see we're not passing in a separate graphics card. We're actually using one graphics card, and we're sharing the graphics resource between the host and the guest system. So you can see that's coming up right now. And while we're doing that, while that Windows VM is coming up, I'll just pull up another program here. This is Tux Racer, obviously. And yeah, I'm going to run the Heaven benchmark while we're at it. So yeah, the main thing that we're doing here is that we're automating a lot of the stuff relating to GPU stuff. We're trying to make it like really easy to use and user friendly, because this has traditionally been a kind of hassle to do, or you've needed to actually buy two graphics cards. One graphics card you pass into the virtual machine, one that you use on the host, and that setup it's been expensive, it's been difficult, it's not really easy to do, it's really time intensive. You can do this, in 20 minutes, you can install the software, and basically will automate the whole process of setup for you. The one thing that we really do want to get to eventually are these things. This is the Intel DG1, their GBPG enabled device. So we really, really had to hack to get this stuff working on NVIDIA, and we even had to do one other thing. Grab. Initially, we started out hacking these W7100 cards from AMD to enable the virtualization APIs in consumer hardware, because it's always disabled. The stuff that's facing. But these parts, these things that are on the horizon, Intel Arc GPUs, they have enabled the ability to do virtual GPU stuff at every price point. Like this is the entry series card. This is available on the really, really low end stuff all the way up to the high end stuff. And I think it's really going to change things. So because of that, we're hoping to see those things proliferate. And we really want developers to help us with libvfio. So we think we can improve things. We think we can make it, easier to use. We can make it better. We can make it better. So please talk to us. We're making it open source today at libvf.io. Yeah, that's essentially the talk. So, thanks so much for taking a look at some of our stuff. Michael, you didn't say much, did you?
No, but yeah, we have currently installing or creating a VM, starting a VM, stopping a VM, LS and PS. The open source version currently only supports AMD GPU, specifically AMD GPUs that is under GIMP driver. Main reason is we're still working on the process of refactoring to handle Intel as well as NVIDIA.
Yeah, the old code was some pretty bad code quality problems, and Michael's gone back through and fixed it all up for us and made it a lot better. So yeah, that's going to make its way into the open source release out of the refactor as time goes forward. But today, if you want, you can download it at libvf.io. We're going to make that live right after this talk. And get started playing with it. And if you want to submit some pull requests to us, we'd love to work with you. So I'm Arthur Rasmussen. Thanks for checking out our talk. And Michael Butchell.
Yes.
Okay. Thank you so much, guys. That concludes.
Okay, the next talk of the day is Another Year Under ISA, Panfrost Update by Elisa Rosenzweig.
You have an open source driver in Mesa for current generation hardware. You have machine-readable documentation for that architecture in Mesa, and you're about to be certified conformant when the vendor of the hardware comes out and deprecates the architecture, releases a new architecture, and doesn't document it or release open source drivers for it. What do? Well, you reverse engineer it, of course, but the vendor does give you one little secret. They tell you that there is operational equivalence between the instructions in the new architecture and the instructions in the old architecture. But wait, you had machine-readable documentation for the old architecture, so there's no new reverse engineering needed, there's no new concepts, no new execution model. All you have to do is map the new encodings to the old encodings. This is certainly a tedious job, and it'll take you a few months of work, but there's nothing conceptually impossible here. And more so, you have the potential to do incredible reverse engineering in terms of the level of detail to go for perfect, not just good enough. You could even match the vendor syntax, confuse them a little bit if you'd like. So great, you reverse engineer it, and what do? Well, you should release documentation for it, or write documentation for it. The vendor was clearly unable to. Maybe they ran out of time. Maybe they didn't understand how important it is to release documentation for their hardware. But being the good, upstanding community member you are, you do the right thing and write documentation for it and publish it so everybody can understand the hardware. And you're really helping out the vendor there with their own hardware. What do you do after that? Well, it would be even better to have a disassembler and an assembler, both open source and upstream in Mesa. And again, being the great community member you are, you write those and upstream them. The vendor will thank you profusely, I'm sure of it. From there, of course, you want to have a full driver written, not just some documentation. How do you manage that? Well, we know that there is this operational equivalence between the instructions on the old hardware and the instructions on the new hardware. And we already have a conformant compiler for the old hardware. So all we have to do is extend the old compiler to produce the new encodings. We can reuse all of the instruction selection and all of the optimization passes with very few changes. So that's all we need. And with another few weeks of effort, you can spin up a prototype targeting the new hardware and upstream that code. And before you know it, you have a Mesa driver upstream for this new hardware, all open source, no mysteries, open documentation, and the hardware vendor only has you to thank for it. This is the story of the ARM Mali G78 with support coming into Mesa now. Thank you.
Okay, the next talk is by Roman Gilk, and that's on the input method hub. Roman, the stage is yours.
Hi, thank you. I want to give you a quick overview about a project or an initiative which is going on in freedesktop.org Valent protocols. It's the input method hub, how it's called. And the idea about it is to assess and document and think about two protocols which there are in Valent protocols: the text input and the input method protocol. And their purpose is to control software composited text, as I would describe it. So it just means that instead of having like a physical keyboard to input text, you have some kind of software component. And if you look at the bottom, you have two examples for that, like a virtual keyboard, or for example, like an input method editor for often Asian languages need this for having to cover all the different characters that there are. So there are already protocols for that in Valent protocols. As said, text input and input method are the main ones. But there are different versions of these protocols, and actually some projects use the protocols from freedesktop.org. Others have different versions of them. So there isn't yet a common standard for that. And the input method hub wants to change that. And what is the input method hub? It's basically an issue ticket in the Valent protocols repository. So just to give you a quick view of that, I already opened it. So that is the issue ticket. And yeah, you can see here, it's, here's the, first of all, some introduction and motivation for you to see, to understand what it is about. So it's the issue ticket number 39, but you will find it as usual in GitHub. There is a description of the challenges that there are, and especially to give you an overview what this stuff actually does. This graphic, I didn't include it in the presentation because you can see it here, and it basically means you have an input method provider on the one side, which is client, and text input clients, which then receive this text which the input method client sent. So, and yeah, you have here some more description of the different protocols versions which there are, right? So there are lots of different ones, and here upstream and downstream. And you have kind of a neat implementation matrix, I would say, because it shows you which project currently implements which standard, right? So we have here version 1, version 2 of input method, text input, right? There is even a rather obscure one, the Qt text input method protocol, which is only used by Qt. So the idea is to put this all together or share or find a common ground to have then a final version of these protocols which can be shared over all protocols. And yeah, that's what the ticket is for. And the current progress is that, as said, the ticket is there to provide an overview of the existing protocols. And we want to branch out version 4 protocols, which already happened, right? There is a work branch for that in the Valent protocols. repository, and we want to collect requirements for the new protocols, right? There is, if you look in variant protocols number 39 issue, going back here into the related issues, right, or linked issues, then you can find here, for example, a ticket which which tries to gather all the requirements which one side of the protocol needs. And there's a lot of feedback already, so it's quite good to see many people interested in that. So the current status, lots of feedback, but only from one side of the protocol yet. So there's not so much feedback yet from the text input side. So that's something to look into more. But there's, interestingly, I learned this today, a Qt prototype for the next text input version, which we are currently working on. So that would be then version 4, right? Or the version which is currently being published on this next branch. So what needs to happen next? I think all this feedback needs to be assessed and documented or gathered, and then we need to find a scope for these new protocols, and we need to create a protocol graph. And I think that could be done by a single document developer if he works on that for 1 month. So that's maybe something to look into very next to push this initiative forward. So thanks for listening.
Thank you very much. Up next is Ricardo Garcia with a quick overview of VK-Ext multi-draw.
Hello, my name is Ricardo Garcia. I work at Igalia, and today I'm going to talk about VK-Ext multi-draw. It's a Vulkan extension that was published this year, and as part of Igalia's collaboration with Valve, I had the chance to participate in its release process by reviewing the specification text in detail and providing feedback, and by creating conformance tests for it in the VK-GL CTS project. So, VK-Ext multi-draw is an extension that was created to cover a gap that existed between the OpenGL and Vulkan APIs. OpenGL has the multi-draw arrays and multi-draw elements draw calls, which didn't have an equivalent in Vulkan. So Mike Blumenkrantz, working as a Valve contractor, created the extension to be able to use it in sync and to ease implementing that part of OpenGL on top of Vulkan. But the extension can be useful for more people and situations, obviously. So with this extension, you can record multiple draw calls without changing a state between each call, using a single function call. So it avoids the typical CPU overhead caused by checking common buffer state, which is draw call. In fact, if you're working on a Vulkan implementation, you can also use this extension as some kind of reference to improve the efficiency of state checking in draw calls, for example. The new APIs introduced by the extension are similar to the indirect family of draw calls, but they don't need GPU accessible memory, so they complement the existing set of draw calls nicely. The extension adds a couple of new draw calls. CMD draw multi is equivalent to calling CMD draw multiple times in a row, and CMD draw multi-indexed is the equivalent when using index buffers. The mechanism is the same in both cases. Given the original draw command function, the extension extracts a couple of arguments to a multi-draw information structure. These will be the draw parameters that will change in each draw operation. You can store an array of those structures in host memory and use that array with the new multi-draw function by passing the number of them and a pointer to the array as arguments to the new function. Then the common buffer, the instance count, and the first instance arguments don't change between draw calls, and they have the same value they would have in the normal draw command function. The remaining argument is a stride that indicates how many bytes to step over to find the next information structure in memory for each draw call. So normally it would be the size of the structure, but you can also use other values. So for example, if you use 0, you only need one structure, which is used over and over draw count times. But you can also use, you can also interleave information structures with other data in memory and then use a bigger stride to jump over the extra data. The equivalent function with index buffers is pretty similar. Some arguments are moved to a structure. Then you use an array of structures in host memory and pass the count and a pointer to the new function. And some other arguments don't change and would have the same value as in the non-multi case, which leaves a couple of arguments to be explained. So the stride is similar to the previous case, and the vertex buffer, the vertex offset pointer is optional and lets you specify a constant value for the vertex offset if you know that parameter is going to have the same value in every structure in the array. This way you can, if you want, you can save some memory and you can also save some CPU in the application and in the driver. The extension had input from more people than the ones you see here, but I thought it was fair to give at least a shout out to Mike, who created the extension and provided the implementations for Anvil and RedV, which I used when creating the conformance tests. Jason from Intel, who was involved since the beginning and reviewed the initial version of the specification, and also to Piers Daniel from NVIDIA, who was involved early in Kronos and reviewed the specification and provided an implementation of the extension outside of MISA, which is pretty cool, and I also used it when writing the extension tests. And with this, thanks for watching and see you.
And now for the last talk of the day, Ethan Lee, Liberty Jubibo, is going to present us the quest for Wayland by default in SDL.
Hello everyone, welcome to my lightning talk, SDL, the quest for Wayland by default. As a really quick intro, I've been porting games for 10 years full-time. My 68th game comes out at the end of the month, so if you want that wonderful golden number coming up next, please email me because that slot is in fact open. SDL is what my entire catalog uses. It's what pretty much every Linux game uses and what every big Linux game engine uses. So like Unity, Unreal, Source, Game Maker's IDE just recently started using it. It's hard to find a game that doesn't use it. And so for SDL, we actually default to X, which is no surprise to anyone. We've been using it for a very long time. But what might be more of a surprise is that we actually have had Wayland support in SDL for quite a while. It just hasn't been considered production ready because there's lots of things we have to do. And we have pretty much done all of those things, except there are a couple that are still pretty major. And we're going to go over those issues today. The big tracker that I sort of threw together in the form of a pull request is in that link. Most of what we have left at this point are just bugs. So like keyboard and text, there are a couple problems that were just caused by me not knowing what I'm doing with XKB common or the text input protocol. So if you're familiar with either of those, you could probably jump in there and fix them in like a day. There are some wish list items, but they're not that big of a deal, so we're not considering them mission critical. Because really, when you actually go and run a game with SDL with Wayland enabled, you'll find the experience pretty much feels complete at this point. We have client-side decorations finally. We have full screen toggling working, high DPI works, input's pretty much there. With a recent desktop and a recent SDL, it feels pretty darn good, except when it doesn't. So we have basically the two major blockers, and the first one you can see right here. The first blocker is OPA presentation, because as it turns out, a lot of games, mine included, use alpha in the back buffer, because we actually do use the alpha channel internally, but we just weren't expecting that compositors might actually use the alpha channel as transparent. Crazy, right? Alpha as transparency? Yeah, didn't see that coming. But problem is there are lots of games that use this, and not all of them are going to get updated, so we need something in SDL that lets us kind of preserve original behavior, because we don't want to tell Wayland to not do transparent rendering, because there are genuine reasons to actually support that. So in this case, we saw that in Vulkan there's already something that basically fixes this, but there isn't an EGL version. So we just decided to make an extension. And by we, I mean Eric, because Eric designed, documented, implemented basically everything. So thank you to Eric for basically doing all the work on this. But yeah, it's in the EGL registry. SDL uses it. NVIDIA's acknowledged it, so it'll be in a driver at some point. The Mesa implementation is done. but we don't have a test. There's an SDL sample that acts as a test, but it's not, as far as I know, it's not sufficient for CI. I could be wrong on that. But if you like making test programs, go to that link. We could really use a test because then it can go in the next Mesa release. Less finished is the other blocker, which is surface suspension. Because basically what happens is when a window isn't visible, the compositor has all the permission in the world to block presentation and stall the program forever, which from an energy efficiency standpoint kind of makes sense because like regular applications using like GTK or Qt or whatever probably don't care. But games absolutely do not tolerate being stalled for any reason whatsoever. Like absolutely zero tolerance. I could go on for a whole hour about why this doesn't work and why there's no way around it. Just know that it doesn't work and we need a way around it. My original idea when I first found this bug was, well, let's do swap buffers with timeout. Like once again, just going back to Vulkan, which has timeout in presentation, let's just rip that off and make an EGL extension. The problem is that, I mean, other than design, like the design isn't that hard, but actually fixing it in the back catalog for all applications, as well as getting Vulkan to use it, because it turns out nobody in the Vulkan world uses timeout, as it turns out. Basically, there's like a lot of reasons why, even though this is a decent idea, in practice, it wouldn't actually fix the catalog very well. Unlike the other thing, which definitely would do a lot better, is something that Joshua Aston from the DXVK team kind of came up with, which is a protocol. It doesn't really change behavior in any way. It just tells the applications what the compositor is doing. So when a window surface is suspended, it just fires an event saying, yes, we're suspended. And when it's back, it fires an event saying, okay, now it's not suspended. It's a very simple protocol. It's very easy to integrate. Like SDL already has a patch. EGL and Vulkan have prototypes that work. And we have, a prototype on the server side too, which is great. Problem is the spec wording, it hasn't been finished yet. Like there's a lot of review going on there. There are a lot of questions about presentation implementations. So like what to do, like, so should we keep the frame? Should we queue them? Should we just drop them entirely and expect that the application will redraw when it's unsuspended? Like there's a lot of very particular details about an extension that really is simple, but there's a lot of scary questions, and smart people are talking about this now. So if you go to that link, you can look at the discussion. I really would like for this to be wrapped up soon because this is probably the most serious bug by far. And we need this to be fixed for Wayland to be the default in SDL. Like it's pretty much non-negotiable. So I'm probably over time. I don't know because I don't have a clock. But basically go to these links if you want to follow me, ask me questions, sponsor me, hire me, all that stuff. Do whatever you want. Thanks for your time and have a wonderful XDC. Thanks, everybody.
And that was the last talk of the day. Thank you very much for attending the day one of XDC 2021. And I'll leave you with some background music for the next few minutes. And then I'll see you tomorrow.